Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving here today, as it is every day, here in my virtual classroom. Stepping inside as we begin Chapter 2 in the Big Ideas Math Integrated Math 3 textbook on linear and quadratic functions. Now, this means a lot of graphs, a heck of a lot of graphs, something that I generally might gripe over. I'm starting now, but over time you hear me go, oh, more graphs. I hope there are more graphs. Oh, there are more graphs. Here we go. Because it's a lot for me. I'm going to do every problem in the problem sets. Hopefully you're doing significantly less for your assignments or whatever reason you're watching me now. And if that's not what you're watching for, you might have to jump to find another video. But what we're going to do is section 2.1 for this particular video on parent functions and transformations. Now, this will speak a little more generally when it comes to the different kinds of graphs we're going to talk about: constant functions, linear, absolute value, and quadratics. We're going to speak on those all throughout this chapter, but this just specifically gets on the transformations. Now, they will have us graph. And I'm going to warn you, when it comes to them doing graphs, and they did this for the IM2 book as well, for absolute value functions, the V-shape, and quadratic functions, the U-shape, they tend to use a table. Now, I don't plan on using a table myself. If you saw me in my IM2 videos, and check out the playlist for Chapter 1 for absolute value and Chapter 3 for quadratic, you'll know that I don't use a table in graphing, and I taught how to do it in a tableless manner. Now, Section 2.1, I will be graphing without a table. I'm going to warn you, I will be graphing without a table. And I'm not going to spend too much time teaching the graphing without a table for this section. The main reason why is because I believe they use Section 2.2 and Section 2, I'm looking at the list, 2.2 and 2.5, I believe they work on the actual here's how you do things without a table and here's how you use the numbers for it. In these cases, they expect you to use a table or a graphing calculator for most parts, I'm sure. So if you're still forced to use a table, if your teacher uses a table, whatever it is, or graphing calculator, follow along with them on those parts and confirm you get the same answer as I do. I will use their examples and explain how they choose the table values that they use and how order of operations work for them to get the values. But when I do my own graphs, no table. And I apologize for that. It's just something I'm not going to bog down my time with. And it's something that I feel that we should be learning as a whole, as I did teach it for the IM2 stuff. So I'll continue that for IM3. So like I said, 2.2 and 2.5 use a little bit more of tableless graphing methods, I believe. I haven't started them yet, I'm not sure. But I do know that this one kind of still sticks with the table portion. So without further ado, guys, I'm going to go ahead and get started. If you want to check out the description section down below, follow alongside. I'm going to start with the lecture portion, but go to the problem set, find the timestamps for that, and you can download also the PDF for this particular section 2.1, as well as graph paper. I'll provide the square graph paper with scales and the tall graph paper because I might have to use them for the quadratics. We'll see how they pan out. I have no idea yet. So without further ado, let's go ahead and check this out and get started. We're going to learn to identify families of functions, the different types that I just mentioned before: constant, linear, absolute value, and quadratic. We're going to describe transformations of parent functions and describe combinations of transformations. Now, the second one, transformations of parent functions, is something we did a lot in IM2, so I don't think it's really different here. I think it's really just a lump sum of everything we did in IM2 in one section with a little bit more exploration, I'm sure. Core vocabulary, again, these are phrases you might have heard in IM1 or IM2 as a whole. Parent function, it's the basic form of something without any transformation types. Transformation, whether we stretch, compress, reflect, translate, things like that. And translation, reflection, and stretch are the next target words here. We can vertically stretch and vertically shrink, all told within here, based on our parameters. Previous values or previous phrases you may have already heard so far together: function, domain, range, slope, and scatter plot. I didn't know that we're doing scatter plots. Okay, so, well, I'll talk about them when we hit them. Okay, identifying function families. Functions that belong to the same family share key characteristics. So, the parent function is the most basic, that's what I was saying, most basic function in a family. Functions in the same family are transformations of their parent function. So, yeah, when you see, and I think the way that I tend to say it, I think I use the word behavior, how that function behaves. So a constant function will always be flat no matter what. This is y equals 1. I would assume y equals 0 would be the most basic form of a constant function, but it's a horizontal line. It's always a horizontal line. No matter how you transform this into a higher or lower value, y equals constant will always be horizontal, period. A linear function will always be a straight line. It may go kind of a little diagonal this way. It may be a negative slope, whatever, but the parent function y equals 1x plus 0, think y equals mx plus b form. That's a linear equation. It'll always be straight. It'll have an all real number domain. Oh, I didn't bring this up before. The range is equal to whatever y values exist. Domain is all real numbers as it goes forever left and right. This graph goes forever left and right, forever up and down, all real number, domain, and range. So all linear functions, even if I change the slope to 1/2 or to -4 or something like that, it's still linear by nature. I can have a plus constant and I can translate it, but it's still linear. It still behaves that way. Absolute value functions with the absolute value symbol right here and the variable inside will always have this V-shape thing to it. It'll have some sort of vertex at the end of the V-shape. Now we may move it eventually or make it narrower or wider or flip it over. Okay, but the parent function, y equals absolute value of x, is just right here, slope of 1 or -1 on both sides of the V, and an all real number domain, and y is greater than or equal to 0, 0 being the vertex. It is not an all real number range. The range is limited by the low end of the vertex or if it flips over the high end of the vertex. And lastly, we have quadratic functions, y equals x squared, varieties of these guys right here. They will be a U-shape. They progressively increase more over time. They don't have a slope. They'll have what's called a stretch factor, which we're probably going to refer to a little bit today, but more in section 2.5, I believe. Stretch factor with an all real number range. It does go forever left and right despite its sharp increase. Y is greater than or equal to 0 because the vertex is currently at y equals 0. But when we start translating it or stretching it or whatever, we're going to change some characteristics. This can also flip over. It won't be a sideways parabola, not this way or that way, but it's going to be one of those 4 ways. So these are 4 of our function types that we have. Later, and I shouldn't be talking about this too much, but just as a tease, later we'll talk about square roots, we'll talk about cubics and cube roots, we'll talk about logarithms, we'll talk about trig functions, sine, cosine, and tangent, and probably their reciprocal functions. There are a lot of different behaviors of graphs that you can talk. Oh, and rational functions. There are a bunch of different functions of graphs we can have. But seeing them for what they are lets you know what kind of one it is. And that's what they're talking about. You can identify which one it is, and then they'll transform from that type. They'll still behave that way, even if they transform. So identifying a function family, you can do it, identify which one it belongs to. This one with the V shape is going to be an absolute value function because it's a V shape. No other kind of function can do that other than the V-shaped one, right? So that's the idea behind it. And then they start to say, compare the graph to its parent function. Remember, the parent function was originally y equals absolute value of x. Now, I think we're going to have to, that's terribly drawn. I think we're going to have it graphed for ourselves quite a bit each time here. I don't know how all the examples are going to go. This one shows the equation as well, but the original parent function was right here. The vertex was at the origin, and its slope, its rise and run, was 1. So it never flipped over, so no change on that, but it did stretch itself more. Instead of going up 1 over 1, it goes up 2 over 1. That considers this thing to have a vertical stretch. I don't think we get to describe it that way yet, so maybe I'm jumping the gun a little bit. But the graph is shifted up. Notice the vertex goes from here to here. Notice that it's narrower as well. That will mean it's vertically stretched. And then we're going to talk about domain as well. Domain is still all real numbers, but the range, instead of y equals greater than or equal to 0, is now y is greater than or equal to 1. Now 1 is the lowest y value that we can hit there. Okay, so there's an example of one of them. It looks like we're not really talking about stretch factors and stuff like that yet. I'm sure we're going to get into them. But V-shape, absolute value, here's the equation. All those numbers will apply later. Note that I do sight read this material. I haven't seen it beforehand, so I'm just doing my best to teach what I think I'm going to see. Okay. Let's move forward. Describing transformations. Okay, I think this is where we start to talk about the other stuff. A transformation changes the size, shape, position, or orientation of a graph. Bigger, smaller, the way that it, like that, how it moves this way, or orientation, it might flip over, right? I can't really flip my hands over, but going from here, say to there, like that, right? A translation is a transformation that shifts a graph horizontally and or vertically, but does not change its size, shape, or orientation. You've done translations. You've done an IM1 and IM2. So we'll talk about them here. Graph g of x equals x minus 4 and its parent function, then describe the transformation. Now the parent function this is a linear function. All you have, x is not being affected. X exists, so it's not a constant function. It's not being affected by an absolute value or a quadratic. Therefore, it is just a linear function, so x to the first. It's got a slope of 1. It's got a y-intercept of -4. Now this one, they're not going to graph using a table. They assume that you learned how to graph y equals mx plus b back in IM1, where you have the slope and the y-intercept. So the original y equals x is just y equals 1x plus 0, straight basic right there. Y-intercept is 0, up 1 over 1. This one also goes up 1 over 1, but from 0, -4. That y-intercept, again, I'm not teaching as to why that is, and they're not even using a table, so they assume, you go up 1 over 1, you draw the graph. So how does one compare to the other? The graph of g of x equals x minus 4 is a vertical translation 4 units down of the graph of the parent linear function. And that's it. It didn't flip over, it didn't stretch, or anything like that, and of course it's still linear, as it will remain. So that is how a translation works. Now, there's a bit of a wrinkle as far as whether we call this one a vertical translation 4 units down or a horizontal translation 4 units to the right. For the sake of argument, as long as it's not inside a function or inside parentheses, we're going to assume it means 4 units down. So even though this one also goes 4 units to the right, you can tell right here that you could argue it goes that way as well. Okay, so that's a translation. All of the translations will be like that. If you saw this one before, this was a translation 1 unit upward. 1 unit upward, that's where the +1 is kicking in. Of course, I'll let the book talk about that more in a bit. Okay, let's look at a reflection. A reflection is a transformation that flips a graph over a line called the line of reflection, or line of symmetry, or something like that. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So here's an example of them using a table, by the way. Here's an example of them graphing a quadratic function and its transformation after it reflects over the x-axis. Now, we recognize it reflects over the x-axis by our version of the graph. Where I'm going to talk more about this negative has to do with it, obviously. But, when you square 0, you get 0. 1 squared is 1, 2 squared is 4. You're going to hear me say things like 1, 1, 2, 4 a lot. 1, 1, 2, 4, 3, 9. These are ways that I graph without a table by knowing those values off the bat. When you multiply by -1, you can see what happens is the positive number turns negative, like so. Obviously, 0 times -1 is still 0. But these numbers turn negative instead. So what's the result here is you have the original parent function, a U-shaped parabola, by the way. It's a quadratic. It's a parabola. So it's going to stay a parabola. But when you plot these y values for those x values instead, what happens? Instead of going up 1, we're going down 1. Instead of going up 4, we're going down 4. So what they said was the same distance away from the line of reflection are the new points after you flip them over. And that's what we're doing. We're flipping them over. Now, they use the table to plot the points. I will not. But the way they did it was a substitution thing, and it's order of operations. Y equals -2 quantity squared. You square -2, you get +4. But when you have the opposite of -2 squared, notice how that's what makes it become -4. The negative here has to happen after you square -2. -2 squared is 4. Opposite of that is -4. So that's how they're doing it by table usage. You can use a calculator, but make sure you use parentheses around it if you do it that way. So again, they use the table, they plot the points, they have the original parent function, its transformed thing. How do they describe it? The graph of P, this new one, the graph of P, is a graph of the parent function, is the graph of the parent function flipped over the x-axis. You may say a reflection over the x-axis, a reflection in the x-axis. Oh, here's where they say it. A reflection in the x-axis of the graph of the parent function. That's their description. That's their final answer after they graph it. So, like I said, they used a table here. They graphed the original parent function and applied a transformation with that. I plan on kind of just jumping straight into it. I apologize. I really do. It's for me sake of time and what I had taught previously. So, you come into my domain, no pun intended, but you come into my domain with the way I teach you, you sign your education away that you can follow what I say, or unfortunately, I might not be for you with that in mind. So I hope I am. Another way to transform the graph of a function is to multiply all the y coordinates by the same positive factor other than 1, because we're already at 1. When we have a parent function like y equals x squared, that means 1x squared. So if you multiply by 1, we don't change its value. When the factor is greater than 1, the transformation is a vertical stretch. When it's between 0 and 1, it's a vertical shrink. I might say vertical compression. Shrink and compression, same kind of thing. Now, they mentioned verticality, and the reason is because whatever we do to x, when we multiply it by 2, y becomes twice as big. Whatever we do to x, whenever we multiply it by 1/2, y becomes 1/2 the size. Twice as big is a stretch on y. 1/2 the size is a vertical shrink on y, given those x's. I plug in 2 for x, I get this for y. I plug in 2 for x, I get this for y. And y is being affected by that 1/2 and by that 2 after you multiply your function behavior by that number. Graphing and describing stretches and shrinks. Let's graph each function and its parent function, then describe the transformation. Once again, so for this one, part A, that's right here. Once again, they use a table. They're plugging in -2 to 2 right here on x, and they get these values out for y. Absolute value does exactly that. So the absolute value of -2 is 2. In a way, it turns the number positive, sure. Absolute value of -1 is 1, etc. And they maintain that. That's why it has that constant slope going both directions. That's why it v's off of that. That's the original parent function. Now, the new function takes whatever your parent function was, and it affects y. In what way? It doubles it. 2 doubled is 4, 1 doubled is 2, 0 doubled is 0, and so on and so on. So everything is doubled. You can see it appears narrower, but the description is everything is vertically stretched by a factor of 2. So it's a vertical stretch. They don't say by what factor. I'll tend to say it by a factor of 2. I thought they would have also described that it's narrower. To visualize a vertical stretch, imagine pulling the points away from the x-axis. I only don't know if I agree with the concept only because our vertex is changing. What I'm going to do when I draw my graphs is I'm going to begin with the vertex, and I'm going to go in terms of that. But that only assumes we have a different translation. Let's look at part B. This is h of x equals 1/2 times x squared. So the x squared graph is still the one in black, and the one in blue is the 1/2. Now, why is it wider? Because what happens is all the y values that you get by squaring these, remember -2 squared is 4, etc. Now we multiply by 1/2. Times 1/2 means divided by 2. Half. Half of 4 is 2. Half of 1 is 1/2. So we're pulling this thing downward. This is kind of what they're saying. The shrink is pulling the points downward from 2 to 1 and from 4 to 2, and 0 is still on 0. So it's a vertical shrink, a vertical compression of your values by a factor of 1/2. That's where they say the phrase vertical shrink. So it's very important when we describe the transformation, we have that phrasing in mind. And vertical matters. There's a difference between vertical and horizontal. I don't think we're playing with horizontal here. It wasn't in our target word stuff. I do remember through tutoring IM3 students last year, though, that we will hit horizontal stretches and compressions. And we can find a way of turning them into vertical stretches and compressions if you know what you're doing with them. Okay, combinations of transformations, multiple of them. You can use more than one transformation to change the graph of a function. Now, this is interesting. This is where they say use a graphing calculator. We can use a graphing calculator. I have one ready. I don't plan on using it for it, but use a graphing calculator. We can go here, y equals, and 3x, and hey, it graphs it and such. Not everyone has a graphing calculator on hand though, and I know how to graph them without one. So I plan on graphing this the same way. You can use a graphing calculator and confirm, validate that what I'm doing, verify that what I'm doing is correct. But I am going to graph the parent function. I'm going to graph the other one as well. I'm going to teach you in future sections how to graph this as the book wants to teach you how to do it. Or you can jump to my IM2 videos in chapter 1. I believe it's section 1.1 that you graph absolute value functions. And then anywhere from chapter 3, I think it's chapter 3. Anything in chapter 3, we graph the quadratics. 3.1, 3.2, 3.3, 4, and 5. We graph quadratics there. So if you want to hear more about it earlier on, go and check those out. Anyway, graph this one and its parent function. The parent function is black. This is the original y equals absolute value of x. And here's this one. Now, there are 3 things that happen here. If you use the graphing calculator, you're going to see several things that happen. Number 1 is it's flipped over. And that's the first thing you probably want to mention. Mention this in order from left to right. Do this negative first, really, and that's how it's being affected. Maybe you don't know that that's why it is, but the negative is flipping this graph over. So it's a reflection in the x-axis because of that. Now, they say followed by. What else is here? Inside the function, this x plus 5, as I do the graph, as if I'm the graphing calculator, you're going to say, well, it went over 5 units to the left, and it did. It went 5 units to the left, and that's what the plus 5 here is for. It kind of sounds backwards with the plus being left, but it is. And then the minus 3 means it goes down 3. And again, if you don't know why that one's normal and the 5 is backwards, that's kind of something we'll learn later. But 5 left and 3 down is the change in that vertex and every other point that follows after it flipped over. So 3 things happen. There's a reflection in the x-axis, a translation of 5 units left, and a translation of 3 units down of the original parent function. Now, we do have to describe the reflection first, but also keep in mind these words matter. Reflection, translation, and then, of course, if we have to, before we mentioned translation, there's also stretch, vertical shrink. Hopefully last example here on modeling with mathematics. The table shows the height y of a dirt bike x seconds after jumping off the ramp. So time 0 is when we jump off the ramp. We're already y feet in the air for whatever reason, because the ramp's 8 feet above the ground, I guess. What type of function can you use to model the data, estimate the height after 1.75 seconds? So what we see here are a table of values from 0 to 0.5, 1, 1.5, etc. They plot those points. Oh, it says create a scatter plot of the data. I thought they meant something else when they said scatter plot. But create a scatter plot of the data. Yeah, so you have points right here. You can tell it has that U-shapedness to it that looks like a quadratic. So as far as identifying it, we can identify that it is a quadratic equation, or at least it appears to be. It's definitely not absolute value, definitely not linear or constant. We haven't talked about constant functions really here. Use the relationship shown in the scatter plot to estimate the height after 1.75 seconds. Your data appears to lie on a curve that resembles a quadratic. Sketch the curve. You can model the data with a quadratic function. The graph shows the height about 15 feet after 1.75 seconds. So here's 1.75. We go and look up at where that is. We're not making an equation out of it, but we're letting our graph interpolate what kind of data that's supposed to show. So it seems like it should be hitting that value of 15. That'd be 15 feet after 1.75 seconds, which is halfway between 1.5 seconds and 2 seconds. So that's how high up in the air the dirt bike should be, or I should be on the dirt bike. I think that's all I'm going to look at there. Let's see. Yes. Okay, we're done with the lecture portion. That was pretty long, but I think it kind of has to be for what we're doing. Let's take a look at these two questions on the vocabulary and core concept check and see what's going on. Number 1, complete the sentence. The function f of x equals x squared is the blank of f of x equals 2x squared minus 3. I assume they mean the parent function. It's the basic version of this thing. It's a quadratic, but 2x squared minus 3 is a transformed version of that parent function. So this is the parent of that. It's basic. There's no change in transformation from what would originally be the most basic version of it. Excuse me. Number 2, different words, same question. Jeez. Which is different? Find both answers. What are the vertices of the figure after a reflection of the x-axis followed by a translation 2 units to the right? Well, let's play with what all these things are, because I wouldn't know. Reflection in the x-axis is flipping. See, you don't need you've probably done this in IM1. You don't need a parabola to transform. You can use a box. You can use a triangle, whatever it is. So this would be a reflection in the x-axis of this guy here, like that. Okay, here's the x-axis. Followed by a translation 2 units right would look like 1, 2. Oh, these didn't follow along. Come here. So that's A. This is what A looks like. Let's see what the next ones look like. Let me just kind of draw a square and see what happens. Okay. What are the vertices of the figure after translation 6 units up and 2 units right? So this is 1, 2, 3, 4, 5, 6, and 1, 2. Ends up in the same spot. It may not have the same corresponding points because reflection technically would have flipped this over, whereas this one just translated up, but it still ends up with the same congruent figure mapped onto the other. So that's also an A. What are the vertices of the figure? Let's get another color. What are the vertices of the figure after a translation 2 units right? 2 units to the right, 1, 2, followed by a reflection in the x-axis. That would still take this and flip it over and bring it up there. So that's the same. So the last one must be different. It must be B. I'm going to guess that already, but I don't know. Maybe I messed up beforehand. What color? Let's use red. What are the vertices of, well, let's use black. What are the vertices of the figure after a translation 6 units up? 1, 2, 3, 4, 5, 6. Followed by a reflection in the x-axis. Oh, that'll bring you right back down to where you were. And that kind of speaks to, that one's different. That kind of speaks to why you want to mention reflections first and translations second. If you want to translate something and match the vertex right at where you want it to be, you got to do that at the end, because if you translate first and then flip something over, it's going to end up in a different spot. Same with stretches and shrinks and stuff. Do that before you describe translations. Okay, guys, I'm going to go ahead and get started with the core problem set. If there's anything you'd like to download, check it out in the description section below. That includes the PDF of the problem set as well as the graph paper I'm going to be providing and probably graphing based off of here. So let's see how we begin. Sorry, I have to get everything set up. All right, so let's go and start. This is problems 3 through 54. Quite a handful, especially if there are a lot of graphs. This is why I'm not going to be using a table, among other reasons. All right, next exercise 3 through 6. Identify the function family to which f belongs. Compare the graph of f to the graph of its parent function. If I recall correctly, they did not really speak too much about the numbers yet. Although, like, because I see the number, you know, I'll probably mention what they are, but I think they mentioned stuff about there's a translation and it's narrower and stuff like that. But they did mention domain and range. So I'm going to make sure to do the same thing here. So this is an absolute value function because it's a V shape. It doesn't matter if I transform it, it'll still remain that V shape. So number 3 is absolute value. Now, as far as describing this, we can say the graph. See, you have to remember what the original graph looks like, and I'm not going to graph it each time, but remember it's an up 1 over 1 kind of look like this. This one appears to be narrower, which indicates a vertical stretch. So the graph, the new graph, the graph appears of f appears to be narrower than its parent function, indicating a vertical stretch. It has also translated. Now, if you count it, it's 2 units left and 8 units down from the origin. So I don't know if I don't recall if they actually said that kind of stuff before, but I am, and we're going to have to do it later. Now, a couple other things I can mention here, and I'll just go ahead and do it right now. Domain and range. The domain of this graph is still all real numbers, and I'm going to use this symbol that kind of looks like all real number stuff. It hasn't changed. It goes forever left and right. The range has changed. The range isn't all real numbers. It never was. Absolute value function has a bottoming out point like this one. It bottomed out at 0 before, and it only went positive. Now the lowest point is at -8, and it goes up from there. So the range on this guy is y is greater than or equal to -8. All the y values exist in that way. And that's all that I can speak on for number 3, or that I believe I'm supposed to speak on for number 3. So let's move on to number 4. So we're not graphing these just yet, right? Now number 4, and they give you the equation, and I don't know if based on the equation you're supposed to know what kind of thing it is, but also the visual. Number 4 is a U shape, and based on the equation being x squared, you'd want to know that this is a quadratic function. It's a quadratic function being a U shape. Now normally, it's a smiley face. It's faced upward. This one faces downward. As indicated, I want to keep speaking on this by the negative that's in front of here. That's what's making it flip over. So the graph of f is flipped upside down from the original parent function compared to the original parent function. Indicating a reflection in the x-axis. Okay, I'm going to begin with that. Now, there are other things that we're going to learn based off the notion of the table that you saw before, that 1, 1, 2, 4 stuff. That's how I'm going to make my graphs. Here's the original parent function. Normally we'd go, and even if I did flip this thing over, it would still have this same stretch, if you will. When it goes over 1, it goes up 1. When it goes over 2, it goes up 4. Well, that's not the case over on this graph right here. When this one goes over 1, it goes down because of the flip, but it goes down 2 instead of down 1. When it goes over 2, it would go down 8 instead of going down 4. This one's narrower than the original one, just like the previous graph. This graph is narrower, indicating a vertical stretch. Now, this factor is the same one that you see. The stretch factor is the same one as you saw in number 3. This one is a 2, and that one is a 2. This one's negative, but that makes it flip over. But the 2 makes it taller, narrower than it was before. But it's a quadratic, so a U shape got stretched. This is a V shape that got stretched. They're both stretch factors of 2. And then there's a translation. The vertex would normally have been at the origin, but now it's 3 units up from where it was. The graph is also translated 3 units up. So again, I might be over speaking on the answers for these ones, but it's things we're going to have to do when we actually deal with our own graphs. So I'm starting it now. Domain is still all real numbers for this new guy, and the range is also limited, but this time it tops out. The highest, before the lowest it could be was y is greater than or equal to 0. Now it tops out at 3, and it only goes down from there. So the range is y is less than or equal to 3. That's the domain and range of number 4. Okay, number 5, a linear function. Now, you may know linear functions very well based on, well, IM1, based on things that you did in the past, and I trust that you do. Now, the scale of this graph is quite interesting. You know, they say y equals 5x minus 2, and it's kind of hard to see, though, like, that's a y-intercept of negative 2? This goes up 5 over 1? What's this? The scale is different. Notice how this scale is going by ones, 1, 2, 3, 4, 5. But the scale goes by fives, 5, 10, 15, 20. Not one of my favorite cups of tea when it comes to me doing a graph. So normally you'd probably see like count up 5 over 1, up 5 over 1. But it's got a slope of 5. A slope of 5 is taller than a slope of 1. That means there's a vertical stretch on this thing. By the way, I should not bury the lead. This is a linear function. It's a linear function. And the slope being greater than 1 indicates a vertical stretch. This graph has a vertical stretch of 5. I know most people want to say slope, and I get it, because it is a slope. It's not a slope. But as we speak more in just transformations in general, we don't say slope as a transformation. The slope, there's a slope regardless of what we do here. The original slope was 1 for the parent function. Now it's 5. That's what we're doing. We're comparing one to the other, and it's stretched. So not stretch of 5, by a factor of 5, based on that, and is translated 2 units down. See, the y-intercept may be 0, negative 2, but it was compared to 0, 0. So this point was translated 2 units down. Every point's translated 2 units down. That's what you have to remember. The whole graph moves down. The whole graph is 5 times, taller than it was. But those are the two things that it compares to. Notice it didn't flip over. It doesn't go downward. It doesn't have a negative slope, right? But it goes that way. Now, domain and range for all linear functions should be all real numbers for both. It goes forever left to right. It goes forever up, down. We good, huh? And the last one, number 6, and it doesn't seem like the examples spoke very much on constants. I think that we just saw one bit on the parent function, but let's go ahead and do one here. So number 6 is indeed a constant function. You may argue that it's linear with a slope of 0, and I get it, but the fact that 0 times x is still 0 means that all you're left with is a constant. That x doesn't change y. X keeps y the same. No matter what x is, y is always equal to 3 on this problem, right? So, but the original constant, which I would have believed would have been y equals 0, they put it at y equals 1. See, I'm more in the mindset of y equals 0 being it. I don't know why they don't do that, but it was originally at y equals 1. Now what? It's moved 2 minutes. It's moved 2 units upward. The graph is translated upward. I don't want to be incorrect compared to its parent function. I don't want to be incorrect and state 3 versus 2 or 2 versus 3 on that one there, but it's translated 2 units upward. There can be no vertical stretch. This graph cannot stretch. It cannot shrink. It cannot reflect. It just moves. It just translates. Or you could argue any of the following could apply. This says a domain of all real numbers as well. None of these graphs don't go left and right forever. Some word problems may reduce its situation there. The range is limited to just one y value. Remember, this equation says f of x means y. This says y equals 3. That's the only y value we can be. Y can't equal 4 or 0 or 3.1. It can't be any 100, negative, anything like that. Y equals 3 is our range. And that's number 6. All right, that gets us started here. Let's continue forward. Already diving into some word problems. I'm sure we'll go back and do our own graphs, but let's go to number 7. At 8 a.m., the temperature is 43 degrees Fahrenheit. The temperature increases 2 degrees Fahrenheit each hour for the next 7 hours. Graph the temperatures over time. T equals 0 represents 8 a.m. What type of function can you use to model the data? Explain. Well, when we have an option of constant versus linear versus quadratic versus absolute value, you probably know by a constant rate, that doesn't mean it's constant, but by a constant rate of change, which one this is. But let's try and do this one for ourselves. Here's time 0. We'll go 7 hours down the line. 1, 2, 3, 4, 5, 6, 7. And let's check out what this would look like. Sorry if it's not equal width exactly. We have 43 degrees Fahrenheit right now. I'll just put this at 43, whatever. And then it goes 2 degrees each time. 45, 47, 49, 51, etc. So I'm not getting too 51, 53, 55. These are all degrees Fahrenheit. 1, 2, 3, 4, 5, 6, 7. All right, so yeah, I'm not getting to whatever with this, but notice it is a constant rate. So what we're doing here is as we increase more and more, is this a quadratic? Does it look like a U shape to you guys? What does it behave as? In this case, if you did it perfectly, which I did not, this would be a linear function. This would be a linear function. Now, it would keep doing that over time, or at least so it seems. It says for the next 7 hours. It does say over the next 7 hours, so let's cripple its domain to that. So if they ask for domain and range, by the way, just as I want to speak on it, domain goes from 0 to 7 hours continuously on X, and the range is from 43 degrees Fahrenheit to 57 degrees Fahrenheit continuously as it goes up over that time. I know they didn't ask about that, but they did ask something else, and they asked, what type of function can you use? It's linear. Linear. Because it exhibits a constant rate of change. Yeah, linear functions, right? You increase the same amount on y every time x increases by 1, or whatever it is. Every time x increases by a constant amount. So there's the graph. There's the result. Okay, let's go to number 8. You purchase a car from a dealership for 10 grand, $10,000. The trade-in value of the car each year after the purchase is given by the function f of x equals 10,000 minus 250x squared. Identify the function to which the family belongs. Now, or to which f belongs. Now, this one does not ask me to graph, and it does not ask me to explain, which is fantastic. Because it is, I'm going to write the equation though, because it is f of x equals 10,000 minus 250x squared. You know, if there's one thing I'm going to bring up here, it's standard form generally rules all in this case. It's probably best that you rewrite this with the highest degree term first, so this guy. And the highest degree term also dictates the behavior, the parent function, the kind of function it is. This is a quadratic because this is an x squared right here. Doesn't matter what succeeds it in standard form, what's after it with an x and stuff. This is a quadratic. This would be a U-shaped graph. Although they're not asking us to graph it, I can tell you exactly most things about what this graph would do by nature, even if you're not expected to know how to graph it just yet or anything like that. Maybe you are. But it starts at 10,000. I'd assume the domain begins. It says you purchase a car for 10,000, so at time 0, it's right there. And then afterward, it just goes down in this quadratic nature. Eventually, it's $0, apparently, after so many years, whatever x represents, each year. So it does something like that. This part won't apply. It's a part of the quadratic function, but it's not part of our domain, things like that. But that would be the nature of it, U-shaped like that, quadratic. We're all done. Okay. Let's go to numbers 9 through 18. They say graph the function and its parent function. Then describe the transformation. See examples 2 and 3. Now, I might pause this video briefly in terms of, I might pre-graph, like I'm going to start one right now just because I see the first one, it's linear. I might get some pre-graphed parent functions ready. So then I can just graph the other one after, and I don't have to re-graph the parent functions each time. The first one, a linear function, has y equals absolute value of x, like this. This would just be the original. So maybe I won't pause. Maybe I'll just speak on them right now and just do that. But I'll have them ready to go as like ammo, just kind of take them and grab them and stuff like that, group them together. So here's one of them. That's my linear parent function. I'll type linear, or I'll write linear. And yeah, that's the original parent function for that guy. So group those guys together totally. Wait a minute. That's all right. And then let's keep doing the same for the other guys. So let's grab another graph. I'm just getting them ready, y'all. I'll probably keep with these graphs. I also have these ones available. These these taller ones right here. Those are really good for the quadratic graphs that go really tall like that. I'll probably leave them for now. I think they're going to stay within a decent window range. Yeah, let's do, I see constants on here, so I'll go ahead and graph a constant y equals 1 on this one. I don't know if I expected to see them or not because they weren't in the examples, but there's a constant 1, getting that ready. And yeah, they seem to have it at y equals 1 instead of y equals 0. I guess you can visually see it. They don't want to block you from not seeing it, but getting that one ready. I might keep these on the side though. So boom, boom. You can't see them. Next one, let's get the absolute value one ready. The absolute value one as a parent function just has a slope of 1, but from the origin, it goes, positive 1 this way, and it bounces and goes like negative 1 that way, like that. So I don't really have to plot the points, but if you do, it's like up 1 over 1, up 1 over 1, like that. So that's that. I said I'd pause this, but now I'm saying I got this, homie. Last one here is the quadratic. Now, the quadratic's the one I'd want to speak on most for you guys, especially when you're like, wait, how are you graphing that so fast, that kind of thing? Because that's the stuff where you might have to wait for section 2.5 for me to get the big nitty-gritty on how that's officially graphed. But 1 squared is 1, 2 squared is 4, 3 squared is 9, negative 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. 1, 1, 2, 4, 3, 9, and reflect. That's the big thing that I do for these graphs here. I'm going to try and draw it as smooth as possible because I got to use it for every quadratic graph that we have. Now remember, this is the parent function. The parent function will also have transformations. We'll translate, we'll reflect, we'll shrink, we'll stretch vertically, stuff like that. But here's the original. That 1, 1, 2, 4, 3, 9 thing, by the way, does not change. Oopsie. It does not change when we multiply by 2 and stuff like that. In fact, we multiply by 2 and stuff like that afterward, after this thing happens. So when I'll say 1 times 2 and 2 times, or 4 times 2, stuff like that, this is a quadratic. I don't think I wrote out the other one was absolute value. Okay, I'm getting these set up. Apologies for the preamble. Let me write for this other one. Absolute value. Okay, I got them all ready to go. Let's figure out which one we're going to pull each time here. Okay, probably should have gotten that set beforehand, but I didn't know what I wanted to do. So, number 9, we have g of x equals x plus 4. Now they say, graph the function and its parent function, then describe the transformation. First thing I want to call out is this thing's linear. With the x involved and all that, this is going to be a linear function, so boom, boom. We're going to do the linear. Okay, so here's the parent function. Let's graph its new one. Now you should know the y equals mx plus b. The slope is 1, just like this one hasn't changed. The y-intercept is 4. So I'm going to be up here, and I'm going to rise 1, run 1 like that. Now, one of the things I do on my graphs, you'll probably always see this, is plot as many points as you can fit or that are within reason of plotting. This is still a slope of positive 1 as I go down and left 1 like that, and it goes upwards 4 units like so. So this graph, I'll do in blue, is the new transformed function. They say describe it. I think what I got to do here is I got to shrink these. So give me 1 second. I didn't prep that either because I'm going to otherwise not have any room to write anything. So let's shrink this guy. All right, so there's the new graph, and describing it, the graph of G is translated 4 units up from its parent function. And that's how I'm mostly going to try and do these. Just kind of use that actual wording that they have for these, and then go ahead and do that. Let me shrink these off. Here, hold on. Let me pause my video. I'm going to shrink these other graphs off to the side. Okay, I'm set. All right, let's move on. Number 10. Y equals x minus 6. So it's also a linear function. Getting that one ready. It's probably not as small as the other one, but I wanted to shrink it just a little bit. So number 10. Oops. So just like the previous graph that we did, this is a y-intercept of -6 this time instead of 4. Still a rise of 1 and run of 1. So I don't think these are the ones that you have the combination of transformations. I think those ones they save till later. This one's going to be a single transformation at a time. Very, very basic beginnings for us, right? They're really starting us kind of on a, hey, let's just make sure we got it down. And I want to make sure you do got it down. But there's going to be the transformation there. So the graph of, oh, I literally wrote Y. Let's actually write the letter they used, F. The graph of F. All right, here we go. Now, F is the blue one each time, or the transformation. The graph of F is translated 6 units down from its parent function, which is linear. It's linear. All right, let's move on to number 11. Now, here's a quadratic function. This is where we start to get into the As long as we have the parent function, I think it'll make a little more sense, and translation still should make most sense here. But f of x, yikes, f of x equals x squared minus 1. So let me steal a quadratic one from underneath you. You should know it's quadratic based on seeing its x squaredness. What I'm going to do is I'm going to take this quadratic function and I'm going to translate it down 1, right? The original parent function looks like this. Now the new function looks like this. Now, as you'll probably use a table, you're going to get the y equals x squared things. 1 squared is 1, 2 squared is 4, 3 squared is 9, whatever it is. And you're going to subtract 1 from them. 1 minus 1 is 0, 4 minus 1 is 3, 9 minus 1 is 8. 0 minus 1 is negative 1, and everything will be 1 less than it was before. So that's why I said if you use a table or graphing calculator, have at it. Go for it. These are the points you're going to end up getting. They'll end up being 1 less than what you had previously. That's why. And this is a chicken versus egg kind of question. I know what they're doing here is they're saying you guys graph it first with a table and let the graph dictate your description of the transformation. What I'm actually kind of doing here is I'm kind of bringing about the egg before the chicken or what have you, just vice versa. And I'm actually doing the transformations. I'm letting the transformations help me understand what kind of graph I make. So remember, if you use a table, have at it, but eventually you're going to have a graph that looks like this, and you're going to say this. The graph of f is translated 1 unit down from its parent function. It doesn't matter that it's a quadratic. The parent function was also a quadratic, so it's still going to behave the same way. We don't have to describe that. We have to say, and then I squared a number and did, no, it doesn't matter. The original did that as well. Okay, let's go to number 12, also a quadratic. The difference here, when you plot points yourself, is you don't square the number and then add 4. You add 4 first and then you square the number. It's order of operations. And it does change the behavior of this graph as well. I'm going to go ahead and draw what that change is. We'll talk about it more. We'll talk about this later. We'll talk about it more, I believe, in section 2.5. So apologies that I'm jumping the gun in a way of doing this, but see if you get these same values. This is going to be my vertex. I'm going to get points plotted like y and y. So you should get the points here. Oh, and here, I'll mention this because I was going to mention it at the time, but they never quite gave an example in a table with that. If you probably noticed when they made their table, I will show you this. If you noticed when they made their tables, they tended to use, for like x and y, they were like -2, -1, 0, 1, and 2. Now, couple things with questions of this, and I'm not going to plug these in, by the way. I'm not going to do the calculations, but you might ask, how many points should we choose to use, and which numbers should we choose to use? Some negative, some positive, and 0? Depends on where your vertex is. Absolute value functions, quadratic functions, you want to build symmetrically around your vertex. And furthermore, something I'm not really talking about right now, if you consider whatever your vertex is, if this was it, you only have to build on one side of it because then you can reflect the points across. Not really going to talk about that, but you can. Here's the thing. This vertex is not at the origin. So in your IM2 skill-based things, you might have to learn how you get vertexes again. You might know that this is the vertex form of a quadratic equation. You might get it in standard form and use negative p over 2a, or you might do guess and check until it works. But if you find out that your vertex is -4, build around your vertex that is -4. So if I did like this, -6, -7, these are the points I plotted right here, right? So -4 was at 0, -3 was at 1, -2 was at 4, -1 was at, like this. These are the points you'll end up getting out in your table. So it's really about how your teacher talks about it. Look, even the book didn't talk about it. I think it assumes that you know some things from IM2. And I'm doing the same thing. I'm building based off IM2 knowledge, and here we are. Anyway, I plotted the points on the graph. There it is. What changed? There's no reflection. It's not narrower or wider, and it didn't translate upward, but it did translate to the left. It did translate to the left, and it went 4 units leftward. So the graph of H is a translation 4 units left of its quadratic parent function. Funkiton. There's number 12. I don't think they were talking about domains and ranges here, so I'm hoping it's okay that I've been skipping that. All right, number 13. Not even halfway through this portion, but maybe after talking about things like that, I can kind of speed it up. Oh, you know what I didn't bring along with me? My parent functions. Let me do that. Give me 1 second. I have them on the side of my frame over here. And silly me, I didn't copy and paste them over. Give me a moment. They're kind of all jumbled like this. All right. Very disorganized. Number 13. I have g of x equals absolute value of x minus 5. Okay. So absolute value is our v shape. This is your parent function. You must graph it alongside this other guy. Remember, the minus 5 is inside of the function. So when you plug in numbers for x, you should choose 5. 5 is your middle value, by the way. Choose 5 as your middle value. When you choose values for x, you subtract 5, and then you take its absolute value after you subtract 5. So the vertex is actually going to be right here. You'll still have this slope of, 1. It didn't flip over or anything. Only thing that changes is the translation. So you should have a graph that looks like this. If you do plug in 5 as your middle point, if you will, then plug in points to the left and right, and you should get a graph that looks like so. And if you do get a graph that looks like so, then you can describe its transformation as a translation 5 units to the right of your parent function. And that's exactly what g of x is doing here. So the graph of g is a translation. Okay. All right, there's number 13. Let's go to number 14. Number 14 says f of x equals 4 plus absolute value of x. Now, it's in my standard, it's in my DNA to rewrite this in standard form, meaning rewrite it as absolute value of x plus 4. Gets my mind right. It shouldn't change what you do when it comes to plugging values in a table. You can choose 0 as your middle value this time. It's fine. And build around that, because this is nothing more than a vertical translation. A vertical translation. And this is translated up 4 units. Compared to the one that was translated to the right 5 units or to the left 4 units or whatever, this is translated up. It's vertical. This is on the outside of that function that you take the absolute value of a number, then you add a 4 afterward. So everything becomes 4 bigger than it was. So I'm doing very, very light descriptions on these things here. I think the difference is when we hit section 2.2 and 2.5, the aforementioned sections I was stating, I don't think we're going to compare them as much to the parent functions. I think we will just do. I'm sure we're going to describe transformations, but I don't know if we have to draw the parent functions those times afterward. Here, we get to compare parent function and then do it. So, the graph of f is vertically translated 4 units above its parent function. I don't think I'm saying that right. I think I should have said is a vertical translation 4 units up. Up compared to its parent function. I think I'm stating that differently than I was before, but that's okay. All right, let's go to number 15. Now we're talking about, multiplying something. In this case, a negative number. Number 15. H of x equals negative x squared. X squared being quadratic. Let's seek out our quadratic. All right, now this was literally an example from the problem set, or from the examples. The negative here is going to take whatever you squared and change its sign. 0 squared, negative 0 is still 0, but negative 1, negative 4, and negative 9 appear here. So everything's flipped over. It's the same distance on the x-axis from what it was before. So that's why we get just this kind of symmetry going down here. So again, this was an example problem. I don't really know how to say it differently. Go ahead and find that example. It was like example 2 or example 3. Go ahead and find that example and you'll see it there. But the graph of h, maybe it wasn't the letter h, but the graph of h is a reflection in the x-axis from its parent function, compared to its parent function. And that's what we're doing right there. Make sure you still draw your arrows and all that kind of stuff. It's just a flipped over version. Once we get combinations of functions, we'll have to do some more things. Maybe we translate after, maybe we stretch, I don't know. Number 16 is also going to be a reflection. Now that I ran out of room on this page, I'll go to the next one once I reobtain all my graphs. Pardon me while I move this stuff over. Let's grab our linear function for number 16. I'm not even a third of the way through this thing. G of x equals negative x. Now you can see why I'm not insisting on using tables. And you're probably going to do significantly less problems than I am. So g of x equals negative x. That's a slope of negative 1 and a y-intercept of 0. This is something you shouldn't have to use a table for, personally, I don't believe. Down 1, right 1 is our negative 1 slope. You can consider it a stretch factor of negative 1. You can consider it a reflection in the x-axis. That's how I'm going to describe it. But it's a slope of negative 1, and that's how I'm graphing it. That's what I know. That's what I do. So there's that graph. Hush. So the graph of G is a reflection in x-axis. Yep. Original parent function went up and right. Now it goes down and right. That's it. All right. Numbers 17 and 18 are translations. You can argue a bunch of different things. I did state it was translations and not vertical stretches and stuff. You could argue it's a vertical stretch. You could argue something reflects here, but I think it's easiest just to talk about a constant value sliding up and down, just moving that way. I think there's more than one answer that's accepted, but I feel like the most appropriate one would be the addition and subtraction of a number. So f of x equals 3 is nothing more than a constant shift of this, and because number 18 is the same, I can get ready to copy and paste this on both of them. So number 17 is going to be f of x equals 3. Now their original parent function was f of x equals 1, so I'm going to stick with that and assume that they're not changing that. And I think this was an example as well. I don't know if that was the exact number, but I think it is. And that's the graph, right? Y equals 3. The graph of f is a vertical translation 2 units up from its parent function. And then I'll just get ready on all this stuff and bring this into basically number 18. So I'm just going to copy and paste this all. Number 18, y'all, f of x equals not 3, but negative 2. So negative 2. Now, negative 2 is down here, so instead of being right here, it's down 1, 2, 3 from where it was before. So 3 units down from its parent function. And then that's the difference there. So it's still a constant, it still does its thing, and that's what we got. Oh, that 17 should turn into an 18, of course. Of course. Okay. All right, that's numbers 9 through 18, where we do basic graphs of a single transformation, and we described it, and we're done. All right, let's see what we got next. Numbers 19 through 26, graph the function and its parent function, then describe the transformation. Okay, it's more of the same, only now it's no constants. We got some fractions. We're going to talk about some vertical shrinks. I got to get the linear, quadratic, and absolute value ones ready. I'll just kind of shift them down a little bit. Sorry, give me a moment. Okay. There's no real change in what we're doing on these. It's just another problem set. So number 19, we have to talk more in terms of like fractions though, but we start with a linear one. So we have y equals, f of x equals 1/3 x. So for us as graphers, as knowledgeable linear equation graphers, y equals mx plus b form, we see this as a y-intercept of 0 and a slope of 1/3, which we get to aptly do a rise of 1 and a run of 3, so we can skip all the fraction stuff in between. So rise 1, run 3, rise 1, run 3. And I understand that that's how we speak on this, which is fine. This can actually speak to us more later when we talk about horizontal stretches, not in this section, but in future sections, as to what we're actually really doing. Very, very fine. All that being said, when we describe this thing, hopefully we can let our description also take hold in the visual of what's going on. We may have said up 1/3, but that doesn't change the fact that we could also describe this as a vertical compression. When we compare the y values of old to what we have now, consider this one. This was at 3,3, and this is at 3,1. This was at 6,6, this is at 6,2. This was at 9,9, this is at 9,3. How do these compare? These got pulled down a third, or to 1/3 of what they were before. They are 1/3 the sizes of the heights of what they were before compared to, y equals 0. This is a third of 3, which is 1. This is a third of 6, which is 2, and a third of 9, which is 3. This is a third of 1, which is a third. right? But we skipped that. We didn't go up 1/3 over 1. We kind of skipped that one, but that doesn't mean it's not there. That's what connecting the dots does. So we still describe this as a linear function that was vertically shrunk by a factor of 1/3. The graph of f is vertically, I'll say compressed. I'm very bad at changing my own habits, even though I'm very aware of what they say. I want to probably stick to what I would say in the past. Is vertically compressed by a factor of 1/3. Now, I don't think they really say that part either, compared to its parent function. I'm probably getting a little more detailed, and I'm sure it's something that your own teacher would appreciate. If I taught it, that's what I'd say. All right, so that's number 19. Let's keep going on number 20. So, even they, and I'm going to keep stressing that, right? Even, let me copy and paste the graphs here. Even they, in the examples, did not use a table for linear functions. I think they expect you to know how those are graphed. But I, personally, expect myself to know how to graph parent and quadratic and absolute value functions without use of a table as well. So g of x equals 4x. You're probably like, stop talking, dude. G of x equals 4x. It's a linear function, so let's do the same thing. It's a y-intercept of 0, and we rise 4 and run 1. So up 4 over 1 like that, down 4 left 1. So that's the slope, sure, it's 4. But it's also a vertical stretch, right? Everything is 4 times taller than it was before, given the same x's. So when x is 1, instead of y being 1, y is now 4. When x is 2, instead of being 2, it's now 8. So everything is vertically stretched by a factor of 4. The graph of g. Like so. 4 times taller. Number 21. Y equals 2x squared. Oops. Okay, quadratic. If you use a table, you can use 0 as its middle for vertex. There's no translation change, at least not horizontal. Well, there's no translation change. We only worry about horizontal translations when it comes to vertex change. But make sure that you square your number before you multiply by 2, right? You do the x squared first and then times 2, not double and then squared. There's a difference. That would require parentheses around it and change everything about it. So 2x squared means we double these heights. 0 doubled is 0, 1 doubled is 2, 4 doubled is 8. This is a good conversational piece as to how I do these, by the way. 1 times 2 is 2, 4 times 2 is 8. Now 9 times 2 is 18, and I can't fit that on this graph. I could do it on those taller ones, but I'm not planning on doing those ones right now. I don't know if I do later in the section. We'll see. Maybe if I devote time to just quadratics alone, like section 2.5, maybe I'll do it. But right here, no. Just going to get this one ready, copy, paste it over. Oh, that happened. The graph of f is vertically stretched by a factor of 2 from its parent function. That's what we're doing. I'm going to leave that on the screen. You can pause it if you'd like to. I'm going to move on to number 22, though, in a second. Okay, number 22. This is where this is where graphing without a table actually gets its, you benefit a little bit, because then you start to really learn what kinds of values you want to be substituting, stuff like that. Now, I still have my original points that I have right here, so don't think that I'm not basing things off that, but I can include some more. The fact that this is 1/3 means we divide by 3. Not every number divides by 3 very well. 1 divided by 3 is 1/3. It's not great. It's a fraction, but I'll live with it. 0 divided by 3 divided by the way, is 0. 4 divided by 3 is not pretty. That's 1 1/3. That's 4/3. 1 1/3. So these are not pretty numbers to use. And you go use this as a table, you're going to be frustrated over the fact, are all these fractions? Not all of them. 9 divided by 3 is 3. So we have this guy here. That's a good one. And in fact, the best numbers to choose are the ones when you divide multiples of 3 by 3. Meaning the ones that you square that are multiples of 3. So 3 squared is 9 divided by 3. 6 squared divided by 3. 9 squared divided by 3. Those numbers are the best ones to use. 4 squared, 5 squared, and stuff, those won't divide by 3. 6 squared is 36. 36 divided by 3 is 12. Now, I can't really fit that on here. It would be somewhere up there, but it would go super tall. Those are really good ones to plot, is my point. 4 squared is 16, divided by 3 is 5 1/3. 5 squared is 25, divided by 3 is 8 1/3. Right, so those are numbers that are worth plugging in if you wanted to add extra ones. Of course, when you use a table, I'm sure you're less likely to be plugging in so many points, but this is how I end up getting points so quickly from here. This is where I definitely benefit from not using a table. And I don't know what they plan on having you do. You know, once again, how many points should I plot? As many as you can fit is my answer. Some teachers will say just 5. Some teachers say 3. I don't agree with 3 for quadratics. You need to understand the behavior of the quadratic and get at least 5. 2 on either side of your vertex, but get the vertex and go from there. The graph of H is vertically compressed, shrunk, by a factor of 1/3 from its parent function. No other change. That was it. It's a lot to do on the problem, but that was it. All right, number 23. H of x equals 3/4 x. Oops. Now, no more quadratics in this set. This one's actually linear. This goes back to what we did before, and not to be intimidated by any fractions when we have linear equations, because you get to count its rise and run. We just got to use 3/4 as the stretch factor and talk about it then. But this is for us an up 3, right 4 thing from the origin, by the way. Up 3, right 4, up 3, right 4. This is stuff that IM1 folks, really savor. They love. They lick their chops over. They say, hey, I know how to do this. So if you're at IM3, you got this one, guys. You got this one. So this one is going to totally miss the points like that until I bring it down. Okay, y equals 3/4 x looks like that. Now, when you compare it to the original function, it is less steep because 3/4 is a number that is less than 1. That makes this a vertical compression. Everything is 3/4 the original height. That's what we say here. The graph of H is a vertical compression or shrink by a factor of 3/4 from its parent function. Sorry, I keep saying compression. I know shrink is the other word that they use, but hey. All right, g of x equals 4/3 x. So what's the difference? In slope terms, up 4/3 instead of up 3/4. In transformation terms, this is a stretch instead of a shrink. It's a stretch instead of a compression. How do we know? Because 4/3 is a number that's more than 1. Right? It's 1 1/3. We just spoke on that on the quadratic problem from before. So now we're going to do from origin up 4/3 like this. Now, if you do end up using a table, which I want to remind you, even the book doesn't do it for linear functions, then you just plug in x. Y is the same as x. When x is, for the parent function, x is 6, y is 6, times 4/3. And a lot of people always ask, how do you use fractions in a calculator? You have to remember a fraction is division. Times 4/3 means times 4 divided by 3. So you multiply by 4 and you divide by 3. But we're taking 4/3 of our values. You can see the blue is taller than black. Therefore, it's a vertical stretch, not a vertical compression, not a vertical shrink. The graph of G is a vertical stretch by a factor of 4/3 compared to, or from its parent function. Okay, number 25 and 26 are absolute values. So no constants in this block of problems. Let me bring over my absolute value one because it's only going to be used for the next two, and we probably have to use a graphing calculator and graph this. Okay, we still have to graph parent function things later. I'll probably pause the video after this one, and doesn't look like I brought my, oh, here it is. Sorry. I'll just get these ready. 25, 26. All right, number 25. H of x equals 3 times the absolute value of x. You take the absolute value of your number and then you multiply it by 3. Boom, like that. So if you learned the graphing thing, listen, you can use a table, put 0 in the middle, that's fine. 1, 1, 2, 2, 3, 3, etc. times 3. You triple 1. You triple 2, like that. Or you can think up 3 over 1, up 3 over 1. Absolute values, because they have a constant rate of change on either side of your thing right here, you can think of it like a slope. Just make sure that it bounces off the slope on the other side. Quadratics don't do this, but absolute value functions do. And I don't want you to mistake one for the other. I think that's why it's kind of nice that we have these together in the same section to understand what one is versus the other here. So the vertex is still at the origin. All of these are based off stretch factors here in this block of problems, right? These are all stretch factor things. None of them are even negative. They're just saying, how do you stretch and shrink? How do you stretch and shrink? And I think it's the one that people have the most trouble with. So it's narrower, but that really means it's taller. That means for each x value, the y value is a taller version than what it was. How much taller? 3 times taller. The graph of h is vertically stretched by a factor of 3 from its parent function. Number 26. I forgot what I was talking about beyond this. I know I was having a different conversation and then I finished the problem. I know I was saying at one point after this set of problems, I'm going to pause and bring back all my parent functions in, because for numbers 27 to 34, it looks like we need to use them again. So number 26, f of x equals 1/2 times absolute value of x. Once again, if you want to think in terms of stretch factor, you divide all your values by 2, your y values by 2. If you want to think in terms of slope, this is up 1 over 2. Up 1 over 2 from either side of the vertex. And the vertex is at the origin. Now, if you use a table, you multiply your numbers by 1/2, which means dividing by 2, right? Times 1 divided by 2. And even dividing 1 by 2 gets 1/2, right? 1/2, 1.5, 2.5, 3.5. These numbers would also show up if you truly wanted to use them. These are what makes these half the heights of what they were initially from the original parent function. That's a vertical shrink or vertical compression of this graph here. So the graph of f okay. So there is number 26. Okay, let me pause this fast to copy and paste over the parent functions one more time. Okay, got them ready on the next page. So let's move forward. Numbers 27 to 34, use a graphing calculator. I'm not going to. You can. Use a graphing calculator to graph the function and its parent function, then describe the transformations. So this is where look at me. I'm the graphing calculator now. Right? Let's go. Yeah, I can't guarantee you guys what all of graphing calculators with this stuff. I'll show you, well, look, I'll show you on a problem where you do all the things, but especially on one that we should already know how to do, like this guy, right? Y equals mx plus b, y-intercept, slope, all that kind of stuff, right? Let me show you on a graphing calculator what you do here. So at least on the one that I have a TI-83 emulator. You might have an 84, you might have a whatever, 89, I don't know which ones they have now. This is a pretty old school one. Y equals, you go to the y equals equation right here to type in equations. So y equals, and here if you want the original parent function for a linear like we have, you can put x. And the other one down here, you can go down and like write 3x plus 2. And then you can graph them. Now, if you want them to have different appearances of graphs, like if I wanted to bold it, I can go to this thing on the side. I can hit enter and cycle through different things, like make it bold. That's cool. As far as window range goes, they tend to go from -10 to 10, which is fine. It's not going to be a squared off appearance. If you ever see teachers do this, there's a reason for it. It's because the pixelation of the TI-83, I can't guarantee this for other ones, but this will square off everything completely, so it goes up as much as it goes right, things like that. So here's the original there, and there's the new one there. So there are the two graphs in comparison, and that's what I'm going to have for my graphs as well. Now, I'm not going to use graphing calculators here on out, because look at me. I'm the graphing calculator now. That's what we're doing for these ones, okay? All right, here we go. So you just saw the answers, and we're going to be doing it. Now, what's the difference between these problems and the ones before? This is a combination of transformations. I mean, this to you is just y equals mx plus b. That's great. Here's my y equals x equation, and here's my y equals 3x plus 2. Y-intercept of 2 and a slope of 1, 2, 3 over 1, 1, 2, 3 over 1, etc. Now, the thing that I want to take home with you on this, though, that will probably apply a little better to nonlinear graphs and our quadratics and our absolute values, is that we can still describe the transformations and you still don't say it has a slope of this and y-intercept of this. We're comparing it to the linear, to the linear parent function. How do we take that thing and make it this? How do you transform it? Oh, you got to make it 3 times bigger than it was, and you got to shift it this way, up 2. That's what we're describing here. So that's where we say, when it says describe the transformations, you, hold on, how do I begin? How did I begin saying these ones? The graph is a. Now I'm just going to say, here's what you do. So vertically stretch the parent. Never mind. The graph of f is a vertical stretch by a factor of 3, followed by a translation 2 units up from the parent function. So now the order of this matters, and I only want to really state it on this one. I might say it on others, but here's why. If I said you translate up 2 first, imagine I take my sorry, I'm trying to, give me 1 second. I'm trying to unlock my original parent function here. It's not working. Okay, imagine I took this parent function that's in black. I'm going to make it green here. Imagine I took this parent function here, and I first did the translation. If I translated it 2 units up first, and then I did a vertical stretch of 3, then suddenly this 2 is going to be up at 6. Right? Because everything's got to be 3 times bigger. Now, when we graph it, we know that we're going to start at 2, and then we do the rise 3, run 1. I get it. But that's us understanding that every point afterward is going to follow. When we instruct something like this, we say times 3 first and plus 2. That's the order of operations. X gets times by 3 first and then added by 2. That doesn't change how we graphed it. We graph in a different order, and that's how I graph in a different order as well for quadratics and absolute value. And I just want to stress that over and over again. All right, let's go to number 28. Number 28 is h of x equals negative x plus 5. Also linear. I wasn't asking, I'm telling you. It is also linear. So, what is this? A y-intercept of 5 and a slope of negative 1. So from negative 5, we go down 1, right 1, despite the fact we're going to describe the reflection first and the translation second. Because if I say we go up 5 first and then I say we reflect over, guess what? That 5 turns into a negative 5. Despite how we graph it together, knowing that we're going to keep 5 as our mainstay thing. So just because we graph it in one order doesn't mean we describe it in that order. Always describe from left to right when it comes to these ones, assuming it's in standard form or it's vertex form or whatever. We'll speak more on the letters, you know, M and B and stuff. We'll speak more on the letters A, H, and K and stuff later. The graph of H is a reflection in the x-axis. If I ever say over the x-axis, that's my own general wording. I know the book says it in. Followed by a translation 5 units up from the parent function. Okay. All right. Number 29 and 30 are absolute value functions. Let's get them going. So number 29, h of x equals negative 3 times absolute value of x minus 1. I mean, listen, I do want to state this. Again, if you took IM2, if you did the IM2 book, if you followed my videos at the time, we're not doing any graphs that we haven't done before. These are pretty solid. Do you remember them? I don't know. But these aren't graphs you hadn't done before. I do want to state that again. So I don't know if we're learning anything new in this section. I think it's just, hey, remember this? Because we're going to do more with it later, I guess. Or we're going to do more different kinds of functions. But all right. So with this one here, again, they say use a graphing calculator. So go ahead and do it. My thing's going to be all about vertex. My vertex is at 0, negative 1. This thing is flipped over and 3 times bigger than it was before. So it's like a slope of negative 3. I get to go down 3 over 1 and down 3 over 1. So again, not over-explaining it, just kind of doing it. You got a graphing calculator, or you're following me. One or the other. Or yes, ChatGPT, I don't know. But there is this graph here. Now compared to the original, 3 things happened. One was a reflection. It flipped over. The other one, next one, it became narrower. It's 3 times taller than it was, only downward. And then we shift it down 1 unit. Even though I started by shifting it down 1 unit, I have to describe it last, just like how it mathematically calculates. All right, the graph of H is a reflection in the x-axis, followed by a vertical stretch by a factor of 3. I don't believe the book ever talks about the factor. And a translation 1 unit down. All right, there it is. Most in-depth description, I do declare. Number 30. F of x equals 3/4 times absolute value of x plus 1. It is an absolute value function. We must transform it. Same kind of bits as before. It's a vertical translation. No reflection this time, but we do go up 1 unit. There's our vertex. And a rise of 3 and a run of 4 from said vertex. We do hit that spot. But then we hit less than. It appears to be wider, or dare I say, more compressed. Indeed. Yes, quite. So this absolute value function, there's a little bit of overlap right there. And right there. And that's what we got for this one. Your graphing calculator should show the same thing if you type it in correctly. So, what is the graph of f this time? The graph of f is vertically shrunk. I'll say the word shrunk this time. No, is a vertical shrink. Is a vertical shrink or compression by a factor of 3/4. Followed, or other random numbers, followed by a translation 1 unit up. Up from the parent function. I'm very bad at typing and talking at the same time. My thoughts, they don't coincide very well. Okay, I'm going to need quadratics and absolute value coming forward, so let me get those two ready because I have them on this page. Copy, paste, keep them over here. Okay, let's go to number 31. G of x equals 1/2 x squared minus 6. Okay, this is a quadratic, yeah? And in quadratics, we got them U shapes. Now, the 1/2, we saw a 1/3 before. 1/2 may be less bad. It depends on who you are. The minus 6 is going to be about the vertical translation. Use your graphing calculator. It's going to show you something. We're going to have a vertex down at 0, -6 like this. Let me actually do this. Let me not start with the vertex. Let's start talking about the 1/2 first, because especially if you're using table bits, right? We square our number. Not that you're using a table, but if you ever do. We go over on x, 1. We square our number 1. We take half of it, which is 1/2. Then everything gets shifted 6 units down. So I'm going to make sure to shift everything 6 units down with this as I go. 2 squared is 4. Half of that is 2. And then it's shifted 6 units down. 3 squared is 9. Half of that is 4.5. And then it's shifted 6 units down. 4 squared is 16. Half of that is 8. And then it's shifted 6 units down. Same thing with the negatives that get squared. They're the same distance up on the other, or excuse me, they are the same amount up when translated the same distance away on that side. So this graph, this isn't where the graph ends up, guys. It's going to be shifted 6 units down. But this is where the 1/2 comes from. It's 1/2 of our previous y values that we had, and then minus 6. What I tend to do is I tend to start 6 units down. Okay? I tend to actually start 6 units down, and then I do these things, keeping in mind what I'm going to do. But let's shift down. 1, 2, 3, 4, 5, 6. So I would generally graph from there like that. And that's what a graph should look like. Now, I can plot more points now that I'm shifted 6 units down, by the way. And I'll go ahead and do that right now. So I'm going to plot some more points that I can fit. How far was this over? 1, 2, 3, 4. Up 8, right? Half of 16. Over 5, half of 25 is 12.5. 12.5 up from 6 is a -6 is positive 6.5 right there. Over 6, up half of 36, which is 18. 18 away from -6 is 12. That won't really fit quite as well. That would be up here. So I can't really fit those, but I'm going to pretend like I could. And then my parabola, boom, like that. Now, this is still a vertical compression. This is 1/2 you know, the heights of what we had before, and it's shifted 6 units down. So there's a lot I could get there. You might have thought I spent a lot of time on that graph. I could spend very little on it as well if I spoke a little less. But I want to try and teach as I go. So the graph of G, and this is probably what you'll see on your calculator, right? The graph of G is a vertical compression by a factor of 1/2, followed by a translation 6 units down of the parent function, from the parent function. Maybe of, I don't know. All right, that's number 31. Let's go to number 32. F of x equals 4x squared minus 3. Now this time I will do, I almost feel like I want the tall graph this time, because this will be tall. I'm not going to be able to fit very many points on here, so oh well. F of x equals 4x squared minus 3. This time I'm going to do how I do. You'll have the graphing calculator anyway, but you're going to get used to hearing this in section 2.5 regardless. My vertex will be at 0, -3. Instead of 1, 1, I'm going to go 1, 4, because I do 4 times 1. Instead of going 2, 4, I'm going to go over 2 up 16, because 4 times 4 is 16. Now, 16 up from -3 is 13, which really can't fit. That's why I'm saying it would have been nice to get the taller graph on here. So that's about 13 up, and same thing on this side. So you're going to see something that looks a lot like this on your graphing calculator. But look at me, I'm the graphing calculator now. Okay, so the tall graphs, right? That's what that one looks like. Okay. Pulling it upward, that vertical stretch. The graph of F is a vertical stretch by a factor of 4. Followed by a translation 3 units down. All right. Okay, 2 more on this set. Number 33. Ooh, big quadratic, a lot of things. Oh, that 1/4 is not pleasant to the eye. That is not a stretch. That is a translation. You even heard me kind of get a little nervous and hesitant with that. I'm like, that's not a stretch. Oh, no. Number 33. How dare you, teacher, for assigning this problem to your students? I have to do it regardless. The students shouldn't have to. Heresy. All right. Let's put it right here. All right, it is a quadratic. Now, a couple things are different. The +3 is inside. Listen, you're going to use a graphing calculator, so I guess that's the one difference. But I don't get to. But your 3 is inside the parentheses here, right? So this will make a horizontal translation because it's not affecting y. It affects what you plug in for x to get the same output of y that you would without it. So this +3 actually means go 3 to the left. My vertex is actually 3 to the left here and then a quarter up. It's a little tricky with that quarter up. It's not going to be terrible, but 1/4 up from where it is, vertex is at -3, 1/4. From here, I do everything that I would have from the parent function, but I reflect. Flip this thing over, stretch factor is 1, so I still get to do my 1, 1, 2, 4 step, just downward. 1, 1, and on this side, 2, 4, and on this side, 3, 9, just a quarter up from -9, and on this side. So, I guess not the worst graph, but fractions are not my favorite. So there's this parabola. It is downward facing. It has some translations going on, but that's it. There's no vertical stretch. So that's what your graph should look like. So the graph of F is a reflection in the x-axis, followed by a translation 3 units left and 1/4 unit up from the parent function, right? I may say that's the vertex, but every point goes 3 left, a quarter up. That's it. All right, last one's number 34. It also has a fraction in the vertical translation. They're not staving away from that. They're like, you're not getting off that easy. Oh, it's not, however, a quadratic. It's an absolute value function. So g of x equals negative absolute value of x minus 1 and the minus 1/2. All right, let's get my absolute value function going. copy, paste. And I don't know what comes up after this. I'll probably have to get my parent functions again later. But for now, let's just see where we go from here. So we have a vertex here at 1, negative 1/2. That's the translations your graph will show. I plug in 1 for x to get 0 out as I would here. So 1, and then negative 1/2, it goes down there. But keep in mind, the reflection technically happened first, which means this graph does flip over. And the stretch factor, or slope, for absolute value is a 1. So, or negative 1. So down 1, right 1, etc. Over and over again is where I'm going this way. And on the other side of the vertex, I'm going to go also down 1, right 1. So here's what your graph should look like when you use a graphing calculator. As I get these going, sorry. Plot as many points as I can fit. Does that have an arrow on it? Yeah, let me get rid of that. Hold on. Keep an arrow on that side. Boom. And again, hopefully we haven't had to do domain and range because I have not been doing that. So that should be this graph here in comparison to the original parent function. So the graph of G. How does it compare? The graph of G is a reflection in the x-axis. Followed by translation. I wish autocorrect was in play. 1 unit right and 1/2 units down from the parent function. Okay. That was an ordeal. Still have 20 problems to go. I don't know how often we have to do the graphs, but let's see what's next. Error analysis, numbers 35 and 36. Identify and correct the error in describing the transformation of the parent function. So I don't know if I have to regraph one. They don't have the original parent function on here, but we still have to know what it looks like. I think we're just stating... Wait. Oh, this is where they call it quadratic versus whatever. Hopefully my graphs... Hold on. My graphs have been showing... I've been saying it out loud, obviously, but they've been saying quadratic absolute value. I hope that's okay that that's there, and that I've been saying it out loud. Here they say in this part. All right. Number 35, the graph is a reflection in the x-axis and a vertical shrink of the parent quadratic function. Now, keep in mind, they aren't saying what stretch or shrink factor that they're going by with all of these, but I don't see a shrink in any sort. Is it flipped over? Yes. But this exhibits the behavior of, without use of a table, 1, 1, 2, 4, 1, 1, 2, 4, just like it would have if it faced upward. This has no vertical stretch or shrink. There's no change in transformation on that. Is it flipped over? Yes. But there is no stretch or shrink. Vertically or horizontal. Stretch or shrink. I was going to put stink of this transformed graph from the parent function. There is simply, here's my correction, there's simply a reflection in the x-axis. I own x-axis. And it's a quadratic. They were right that it's a quadratic. So I hope that's okay. All right, number 36. The graph is a translation 3 units right of the parent absolute value function. So the function is f of x equals absolute value of x plus 3. Now, I don't know to the extent that you're supposed to know how to write equations for these things and things like that. But as we've seen some equations with things inside of there at the time, the x plus 3 portion is the incorrect part. If we're translating 3 units to the right, that means when I plug in 3 for x, I should get 0 for y. But when I plug 3 for x right here, 3 plus 3 is 6, absolute value of 6 is 6, you get y equals 6. Well, that shouldn't work. I should be getting 0 for y when I plug in 3 for x. How? If this was a minus. If this was a minus, 3 right there. So it's an opposite effect when it's inside the function of what you have to negate, to counter the thing that you need to keep y the same for this x, whatever. If I want this graph, I need that to say x minus 3. Now, is this an absolute value graph? Yes. They're correct on that. Is it translated 3 units to the right of its parent function? Yes. The equation is wrong. Their equation is incorrect because f of x because if they input 3, their output would be 6. Instead of 0. A translation to the right results in a subtraction of the inner parameter of your function. So it should be, instead, and I'm not going to type it, I'm going to write it. Instead, it should be f of x equals absolute value of x minus 3. Kind of an interesting question, though, because they haven't really brought on us coming up with equations from functions yet, right? But we could test it and see what part. Every other part of this felt right. That's the only part that's wrong. So, all right, let's keep moving forward to, whoops, nothing, to number 37 and number 38. They have things that look like IM1 to us. Find the coordinates of the figure after the transformation. All right, I get to copy and paste these. You can use the graph paper as provided to copy and paste this as well, or to redraw what's here. But we're going to translate this guy 2 units down. So this is very IM1-like, and I'll even use prime notation on these things. So translate C 2 units down to get C prime. Translate A 2 units down to get A prime. Interesting questions here. Translate B 2 units down to get B prime. And now you have a new graph A prime, B prime, C prime that looks like this. Here's the thing. They didn't ever officially state, and here's where I'm very curious about this. They didn't ever officially state to graph it, did they? They just said find the coordinates. So maybe they're having you practice a little bit more of you take your y values, whatever they were, and you make them 2 less from what they were. When you translate 2 units down, that means your transformed graph is taking whatever you had and making them 2 less. Taking the y values and 2 less. So A was at 2, 1. A was at 2, 1. A prime is at 2, -1. That's 2 less than the 1, right? So that's kind of what I'm thinking as far as what they want you to do with it. But A prime's at 2, -1. B prime is at -1, -4, and C prime is at 2, -5. 2 less on the y's than you had previously. So that's what I'm curious about. Do they want you to do more of the equation basis of it, right? Maybe that's what they want you to do. What's this random 3 doing here? Oh, that's for the next question. Speaking of which, we're on the next question. Let's go. Number 38. Number 38, let's reflect in the x-axis. Now, reflecting in the x-axis, again, on a visual level means take everything and flip it over, which I'll do after I copy and paste it. But it also means take your y values and change their sign, right? Make them negative. So I can say this in one of 2 ways. I can go more of an equation basis. If I say, hey, my new equation's based off this, takes your original y values and it makes them negative. Or it changes their sign, right? So what was A before, reflecting the x-axis from -1, 3 to -1, -3. Here's A prime, let's make it green. To -1, -3. B was at 1, 3, now it's at 1, -3 for B prime. C prime, instead of -1, 1 is -1, -1. And D prime is, instead of -3, 1, it's -3, -1. So like that. Connect these dots here. Because here's the thing, right? Every point reflects not just these ones, but these are the ones where they say, find the coordinates of the figure, the A, B, C, D, or A prime, B prime, C prime, D prime. Let's get them ready and solved. Again, kind of interesting because they're like, IM1 does this, you know. A prime is at -1, -3. Good start. B prime is at 1, -3. C prime is at -1, -1. D prime is at -3, -1. Okay. That's how I imagine we do those ones. Let's move forward. At least they were quick. In exercises 39 to 44, identify the function family and describe the domain and range. Use a graphing calculator to verify your answer. I might use a graphing calculator here just so I don't have to graph it, because they're not asking us to graph it. They're asking us to verify your answer from the calculator. So I think here you're starting to learn more and more what this behavior should be based on the parent function type and the transformations that are done. So on number 39, you have g of x equals absolute value of x plus 2 minus 1. What we should start recognizing here is, first of all, it's an absolute value function. Absolute value. So that's part of it. Identify it. Whoopsie. identify what kind it is. Based on the kind that it is, we want to know. This is true for all sakes of graphs. We should know. It's a V-shape, right? Now, let me just do it this way. I'll do it in kind of a basic way to start with, okay? So, hold on. All right, it's a V-shape. Now, did it flip over? No. Did it stretch or anything? No. When they're asking about domain and range, will the stretch parts matter? Not really. Flipping over may. Did it translate? Yes. Where did it translate? Based off this, you're going to learn that's 2 units left. 1, 2. Based off this is 1 unit down. 1. So this is our new graph based off that thing here. This is at -2, -1. The important part for range is the y value that we bottom out at. So I won't use a graphing calculator, I guess, if I can do basic ones like this. But the domain is all real numbers. We are not going to change the fact that this graph still goes forever left and right. The range is now y is greater than or equal to -1. Before it was y is greater than or equal to 0. But now it bottoms out at -1 instead based off the appearance of this. Graphing calculator, look at me, I'm the graphing calculator now. And that's the one for number 39. Number 40. So basic graphs, right? Not a huge set of copy-paste compared to the parent function. None of that. All right, so number 40. h of x equals x, absolute value of x minus 3, and then plus 2. Once again, this is the absolute value family, V-shape. Okay? So, this time I'll make the axis black and the graph blue. So, here's my original parent function for this guy. Very poorly drawn. Apologies. Let's do some things with it. Is there a reflection? No. Are there translations? Yes. It goes 3 right. 1, 2, 3. It goes 2 up. 1, 2. Again, probably something you learned at the time for vertex form for these things. So the vertex there is at 3, 2. It still goes upward, which means it bottoms out, which means the range is limited at the bottom, not the top. Domain is all real numbers. No change there. I don't expect any changes on those. Range is y is greater than or equal to 2. The lowest y value you get is 2, and it goes up from there. Confirmed. Number 41, linear function. I think that you think that we all think that we know this answer, and that would be very great if we did. Y equals, or g of x equals, 3x plus 4. It's a linear function. This is the y equals mx plus b slope-intercept form kind of thing. And these graphs, in a general sense, would have just looked like this. Boop. But y equals 3x plus 4, starts at 4, and then it goes up 3 over 1 and down 3 left 1 like that. Boop. Now, it goes forever left and right, but it also goes forever up and down. You should expect all linear functions to do this if the slope's not 0, and if it's not a vertical line. If the slope's not 0 or undefined. The domain is all real numbers. The range is all real numbers. They don't say explain. They don't say officially graph. They just say confirm it, and that's what we have. Number 42. F of x equals -4x plus 11. Once again, a linear function in the linear family. And not much to state on this one. The plus 11 is okay right here. And it's a negative slope, sure. But still all real number, domain, and range, right? It's very sharp there, but it goes forever left to right, goes forever up, down, all real number, all real number. We are set on number 42. Okay, really, honestly, look, that's it. That's all we have to do. Number 43. And 44, these are quadratics. So f of x equals 5x squared minus 2. Once again, one of the things you're going to learn whether you're using a table, whether you understand it now, first of all, it's a quadratic. But what we're going to be learning from these quadratic things, whether you use a table or not, is regarding domain and range. The vertical stretch isn't going to affect it. It's what you do after from the translation portion. If I don't translate and I make this thing 100 times taller, the vertex is still at the origin. It's still at 0, 0. There's no change on that. What changes is based off translation. This can go as tall or compressed or flip. Well, flipping over does matter as far as whether you go up or down. But this -2 is what matters here. It goes down 2, and it may go super tall, stretch factor of 5, great, but the vertex is at 0, -2. It bottoms out at -2. Whether that stretch factor was 5, 1, or whatever. So, domain, all real numbers. This still goes forever left and right, even though it goes very tall. Doesn't mean it doesn't go forever left and right. You can plug in any value for x. Range, the smallest y value you get is -2. Okay. And I'll stay on this side with the no lines here. Number 44, we have f of x equals -2x squared plus 6. Once again, a quadratic. One difference, and an important one. What is it? Well, it's still a quadratic, but we turn that smiley face into a frowny face. This graph flips over. So -2x squared like that. Now plus 6 means 6 up. 1, 2, 3, 4, 5, 6. And it goes up here. It may be taller and it may face downward, and the downward part matters, but the translation of 6 upward does not change in that regard. So this is, and where I'm at odds is trying to figure out when the book even really technically taught you this. Hold on. Y is less than or equal to 6. I'll talk about that in a second. I kind of, stress over this idea of like, when does the book teach you this? When did this example hit? When did they really talk about the official thing of do this without a table? They didn't say use a graphic. They said verify the graphing calculator, but they didn't say use a graphing calculator to graph it. The answer to me is from IM2. So that's where I go back to, what did you learn from me in IM2 if you did? If you're new to me here, hopefully we're getting a good sense of this, or you can understand from your own table so far. Maybe it's pattern recognition from earlier problems. Okay, let's move on to number 45, and I'll go to the next page. We have 10 more questions to do. Modeling with mathematics. How long have we gone so far? Hour 45. This will be a 2-hour plus one. Modeling with mathematics. The table shows the speeds of a car as it travels through an intersection with a stop sign. What type of function can you use to model the data, estimate the speed of the car when it is 20 yards past the intersection? So at displacement from sign in yards, it's 100 yards before the stop sign, and then at 0 yards is at the stop sign. That's why its speed is 0. So it's slowing down, it hits 0, and then it speeds up again is what we have here. This is one of the things, I might use the tall graph thing here this time for a couple reasons. One, to get some good, well, I don't really need the tall one. I can use this one. But I do have to change the scaling on this. And here's the thing, I don't need the bottom half of it. Do we even have to graph it? We don't have to graph it, but I think we should. You know what? I think we have to graph it. I think we should. Unless you know how to come up with the equation, and you know what kind of equation it is. Think about what a car might do here, though. Can a car just halt to a stop, boom, like that, and come back up? Is it just going to keep bursting through the stop sign? What's it going to do? Well, let's change this to 100. Oh, this is speed. Yeah, 40. That's fine. Let's change this to 150 and things like that. We're just changing the scale. -50, -100, 50, and 100. All right. X is displacement in yards. So we're at -100. We're at 40. So -100 yards from there, our speed is 40 miles an hour. And then -50 yards from it, we're at 20 miles an hour. And then 10 yards from it, this is 10, we're at 4 miles an hour. And then we stop. And then we go this way. I anticipated this to be a quadratic function. This looks absolute value like. So, okay. And it is an absolute value function. So when you get multiple points, you can really get that idea of, I was expecting this to be a quadratic. I expected you to kind of slow down more over time, stuff like that. But I just realized this is not time. And I don't know if I can extrapolate here, so I'm probably not going to use arrows. My domain, as far as I know, stops when I hit the 100 yards. So, okay, that makes a lot more sense because it's not time. Okay, so what type of function can you use to model the data? Absolute value. Okay. Estimate the speed of the car when it's 20 yards past the intersection. So 20 yards past the intersection is when x is positive 20 right here. We're going to go to our graph and take a look at that. So when x is 10, 20, we estimate about right here where we're at with that. It didn't quite probably hit 10 miles an hour yet. It's probably not till about this part at 25. So at 20, it's a little bit less than that. I'd say if you understand anything about rates, you might see that this should be 8. right? This is direct proportionality. When this is 10, this is 4, double that, double that. So I'm going to estimate based on my version of my graph here. And I probably should have scaled these by 20s instead. But here, that's going to be about 8. So let me type it. About 20 yards from past the intersection. The speed of the car is estimated to be 8 miles per hour. Yeah, I think the one thing I would have changed on this probably next time is changing my scale of this one to go by 4s. So I could end this one at 40 miles per hour, put 20 here, and then you'd clearly see the 4 here and the 8 here. And I think you'd clearly see that it actually hits that. So sorry, I didn't have any foresight of that problem. But I also didn't know it's going to be absolute value. Go figure. Number 46, thought-provoking. In the same coordinate plane, sketch the graph of the parent quadratic function and the graph of a quadratic function that has no x-intercepts. Describe the transformations of the parent function. I thought they meant the same coordinate plane as this problem. I'm like, what are you talking about? Okay, they're saying take a coordinate plane for this particular question and sketch the graph of the parent quadratic function and the graph of a quadratic function that has no x-intercepts. So, can I just take my old... That's okay. I'll redraw the parent function. So parent function 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2, 4, negative 3, 9. Boom. So here's my parent function. Now I can do a lot of different things with this. I don't know if you're ready for some of those things. Now they say no x-intercepts. Remember, this has one x-intercept. It hits the x-axis there. How do quadratic graphs not hit the x-axis? If I move it just to the left, it'll still hit here. If I move it down, like here, it'll hit it twice. How do I not? Well, I can be above it when it goes up, or I can be below it when it goes down. So I'm going to do multiple things to this thing. I hope you're okay with that. Oh, we're not writing the equation. We're just describing the transformation. So let me do all of the things that I can. I'm going to do it right here. I'm going to have this point, and I'm going to put fraction-like things. It's going to be, this is a terrible graph for you guys to follow along with, but this is very open-ended. I forget thought-provoking questions. When it says thought-provoking, that generally means it's an open-ended thing. Do what you want to with it, for the most part. Okay, let's see if you can describe this one, guys. There are several things happening here. I'll even write the equation for you after we come up with the thing. Now, this has no x-intercepts. Does it have a y-intercept? Yes. All graphs with an all real number domain will always have a y-intercept. It should pass the y-axis right there. They didn't ask that. They said no x-intercepts. So let's move this thing a little bit. It's a little close to my typing that I want to do. Actually, I never shrunk this graph, so I might have to, I might have to shrink it. Hope we can still see what's there, though. Okay. So, what happened? First of all, it flipped over. The graph of, I'll call it F, is a reflection in the x-axis from the parent function. Now, what else did I do? There were translations, but that doesn't come before the vertical shrink. Followed by, let's see if you can notice this. I went, here's my vertex. Now I know that you can't see all the things beyond it, but I went, see, normally it's 1, 1, 2, 4, 3, 9. Now it's 1, 1/2, 2, 2, 3, 4.5, 4, 8. I'm taking half of what I had before. It is shrunk vertically, followed by a vertical shrink. Shrink, vertical compression, by a factor of 1/2. Now we talk about the translations. And translated. 4 units right and 1 unit down. All together, we get the following equation, if you're curious. F of x, we do it in blue. F of x equals, not that they asked for this, negative 1/2 times x minus 4, quantity squared, it's a quadratic, minus 1. It's a lot of negatives, and that is my equation. That's actually, I don't know why I'm boxing that. The answer is this part here. Okay, that's my open-ended number 46. Do what you will and want to with that. Hopefully you're learning off these things, and sections 2.2 and 2.5 will be much better. Perhaps I'll be over-explaining at that point that you'll be like, I know what it is now. I don't know why you're teaching it this way. Number 47, using structure. Graph the functions f of x equals absolute value of x minus 4 and g of x equals absolute value of x minus 4. Are they equivalent? Explain. They may be equivalent, but it's by accident that they would be. Or they may not be equivalent. Oh, I'm sorry. This is absolute values. They will not be equivalent. If they were linear functions, they would be. Okay. F of x equals absolute value of x minus 4. I'll do in blue. And g of x equals absolute value of x, then minus 4. I'll do in green. This is where... This is where things change. This is where you have a difference in what's going on with the top one has to do with horizontal translations because now x is being affected differently. I have to plug in different values of x to get the same value out of y that I would compare to the original parent function. Here, when I plug in values for x, I just get what I get, and then y gets affected by becoming 4 less than what it was. This one is a translation of 4 units to the right of the original parent function. You go 1, 2, 3, 4 to the right for the vertex. The green one is a translation 1, 2, 4 units down from here. Like I said, if this were a linear function, these would be the same. These would both cross through the same part. Because they're absolute values, they're different. These are the vertexes. This is where they bottom out. Everything else is the same as the parent function from here. Up 1 over 1, up 1 over 1, like that, on this V shape. The green one also has an up 1 over 1, but it starts from down here. Now it's going to hit all those points, so I'll leave them as they are, and then this goes up 1 over 1 here. So there's some overlap. They do intersect in some of the same spots once you hit x equals 4 and onward, but they are different graphs. They are different graphs. So the green is, this guy here. And the blue is this guy here. So like I said, overlap of those two parts. It's probably best that I just have it like that. They say explain why they are not equivalent. So they are not equivalent because parameters inside the function affect your inputs. So like in blue, right? It changes, right? I have to plug in 4 for x to get 0 for y in that. Well, it's true for the other. But I have to plug in 4 for x to get the same y as I would if I had the original parent function. Whereas here, parameters outside the function, and they don't just affect the input, they affect what you choose for your input in an opposite way. The x minus 4 means I go 4 to the right. Parameters outside the function affect the output. In green, if you will. So, yeah, there's a massive difference between that. Something I probably get to talk about more in different sections, but that's your test. You probably get to use a table if you're doing the official thing for yourself, minus my assistance. Okay, last page of sets, or two more pages, I suppose. Number 48. How do you see it? Well, consider the graphs of f, g, and h. F is black, g is red, h is blue. Does the graph of G represent a vertical stretch or a vertical shrink of the graph of F? Explain your reasoning. I imagine F looks to be the parent function of a linear equation. G is less than when it comes to its rise and its run. So part A would say G is a vertical, not AG. The graph of G is a vertical, I'll use their word, shrink of the graph of F, because it has lesser y values for the same x values. That's kind of the way I'll say it, right? Vertical shrink by a factor of 2. Twice as small here. Instead of 2, 2, it's 2, 1. Instead of 4, 4, it's 4, 2. That kind of thing. Part B, describe how to transform the graph of F to obtain the graph of H. Well, for you might use slopes to figure it out. best. F is just up 1 over 1. H is down 2 over 1. So there are two things that are happening. The down part is the reflection. So reflect H, the graph of H is a reflection in the x-axis. It's a slope of -2, but it's a reflection in the x-axis, followed by a vertical stretch by a factor of 2 from F. So compared to F, how do you make 1 turn into -2? You multiply by -2. The negative is the reflection, the 2 is the stretch. All right, number 49, making an argument. Your friend says two different translations of the graph of the parent linear function can result in the graph of f of x equals x minus 2. Is your friend correct? Explain. Your friend is correct, and this actually goes back to my number 40. I think number 47. The number 47 question on absolute value that I didn't recognize was absolute value first. There are two different ways you can look at f of x equals x minus 2. You can either look at it as f of x equals x minus 2 or f of x equals x minus 2. Now, the parentheses, are the parentheses doing anything to my numbers? Not really. When you consider everything else around it, though, this would be like a 1 times that. Stretch factor is 1, doesn't change that, right? But you just saw in absolute values how an inner parameter changes our inputs, whereas an outer parameter changes our outputs. This says you plug in some number for x and the y becomes 2 less than what it was. This says you have to plug in x's that are 2 greater than what they were to match the same y's as they were before. So the question is, are they the same, or are they, and clearly they're the same because they make the same equation appear, but how do these things make the same answer? Let's look at a graph. Let's take a look at the graph thing and see what happens. When we compare all the differences here, if we look at them as this, look at the first one as just a parent function, if you will, or a way of saying a y-intercept of -2 and then a slope of up 1 over 1. So like this, boom, boom, boom. I'm just going to kind of graph it, right? So we get like this guy right here, yeah? Right here. Okay, there's the original black. Now, blue, let's use blue as a way of, let's take our original parent function, y equals x, right here, and then let's translate it 2 units to the right, right? That's how I see blue. I see translate 2 units to the right, 1, 2. Okay, it makes that graph. Now let's take the green one, let's take the original parent function, and let's translate it 2 units down. 1, 2. You end up in the same place. So your friend's correct because there are 2 different ways you can consider it. You can consider it as a translation 2 units to the right or a translation 2 units down. Either way, the linear function gets you the same result. So that's kind of how I'm going to explain it, or that's how I did explain it. But my friend is correct because I can either perceive this linear function as translated 2 units right or translated 2 units down. Either way, the graph still has the same graph. Still is the same. Hopefully what I showed also works that out. You get the same graph. Because the domain's still all real numbers. Right? The domain's still all real numbers. That doesn't change it. Okay, 5 more questions. Number 50. Drawing conclusions. What is that? Oh, that's people. I thought that was an animal. Like in water. I was like, what are we looking at? A person swims at a constant speed of 1 meter per second. What type of function can be used to model the distance the swimmer travels? If the person has a 10-meter head start, what type of transformation does this represent? Explain. Well, this is a lot like the temperature one. It should be linear because there's a constant rate, just like before. They don't ask me to explain it, so I guess I won't. But constant rate means that we're talking about a linear equation. So number 50, I'll let the question be what it is over there. So constant speed of 1 meter per second. I'll write that. Constant speed equals linear function. If the person has a 10-meter head start, what type of transformation does this represent? So a 10-meter head start, this would be like taking an original equation, y equals x, and this is truly y equals x because the 1 meter per second would be like that. But also, you know, if I have a g of x that's a transformation of it, the 10-meter head start, is that 10x? No, because that would be 10 times as fast as you're going before. You're not 10 times as fast, you're just 10 meters ahead. So that takes your x and adds 10 to it, right? So it's like that. It's like take this graph that you had to start with and instead be up here. So you're going the same speed as people before, you're just ahead of them to start with, right? You'll stay 10 meters ahead. That's not going to change. It's not like you're speeding up. It's not going to look like this, 10x, where you're speeding up as you go along. So this, what type of transformation is that? As far as a graph goes, it is a translation. A 10-meter head start is equivalent to a translation 10 units up from the parent function. So that part's new compared to the temperature question we had before. Okay. Number 51, problem solving. 3 parts. You are playing basketball with your friends. The height and feet of the ball above the ground t seconds after a shot is released from your hand is that's a long sentence. Is modeled by the function here. And if you've done any word problems with me before, by the way, I have a huge thing on quadratic word problems. I'll put a card somewhere. I haven't done it before, but I'll put a card up above right here. I have a huge explanation on all things quadratic word problems. But that -16 thing is there on purpose, just so you know. It's modeled by the function here. So f of t, and if I don't put a card up here, because I might not know how the cards work, I'll put something in the description section down below. The card should be fine. All right, f of t equals -16t squared plus 32t plus 5.2. I'll tell you everything about this right now if they don't ask me to answer it. Oh, they are going to ask me to answer it, so never mind. Without graphing, identify the type of function that models the height of the basketball. Well, part A, it's a quadratic function. The t squared, and this being in standard form, this t squared meaning that's what's dominating it, quadratic function. Now, if I did graph it, it'd be an upside down U shape. That's what it would be. All right, shot of the ball. Part B. What is the value of t when the ball is released from your hand? Explain your reasoning. These are the ones where it says the height of the ball above the ground t seconds after, etc. This is where you have the value of t when the ball is released is t equals 0. Now, this also means that our domain should be everything t greater than or equal to 0. We shouldn't do all real numbers this time. Anything before times 0 does not apply to our shot. T equals 0 is the beginning of the arc and the gravity thing that's taking hold. Otherwise, we're just holding onto the ball or dribbling it or whatever. But t equals 0. They say explain your reasoning. This is just the time for which the model starts to apply itself. It says t seconds after the shot. I guess that's why. Their description takes care of it. The description of the problem's description states the model is applied t seconds after a shot releases hand. Times 0, t equals 0, represents the initial time from when the ball is released. Perfect. All right, part C. How many feet above the ground is the ball when it is released from your hand? Explain. I'll do you one better. I will. Instead of explain it, I'll calculate it. Times 0 is when it's released, so let's do f of 0. Let's do -16 times 0 squared plus 32 times 0 plus 5.2. And I'll tell you what, this problem doesn't do as much in quadratic word problems as my quadratic word problems thing does. We talk about vertex, we talk about time it hits the ground, we also graph them. So none of these really apply anywhere to this except what I wanted to talk about with how this number, how this number, and this number are represented. We're not going to get to answer all 3 in this question. We just get to answer one of them, the last one. -16 times 0 squared is 0. 32 times 0 is 0. And 5.2 added to those is 5.2. F of 0 equals 5.2. That means how many feet above the ground is the ball once released from your hand? 5.2 feet above ground. Let's see. Let me type this. The ball is releases from your hand 5.2 feet above the ground. So I just want to state a couple more things that are just of interest to me, although it probably has to do with future problems here. That's my explanation, right? The math, this is at time 0 when I release it, so that's how we get the number. So a few things I wanted to state here. Negative 16 is a component of acceleration of gravity, the force of gravity on Earth in with feet in seconds. So this is a gravity component. That's why I'm saying it's not a mistake that it's there. This is the initial velocity of the shot in feet per second, upward velocity, initial velo, and this is the initial height right here. So gravity takes hold based off this number here. That's what makes the ball go down, right? That's what makes it, remember, when we take the shot, it's going to be like this, it's going to hit a peak and it's going to go down, whatever. 32 feet per second is the initial upward velocity. Obviously, it slows down over time to hit its peak and stuff, gravity, and it's 5.2 feet in the air. And that's what those numbers are and what they mean. Anyway, moving forward. Number 52, modeling with mathematics. The table shows the battery lives, the battery lives, okay, of a computer over time. What type of function can you use to model the data, interpret the meaning of the x-intercept in this situation? I could tell you what the x-intercept means right now, but I'm not going to just yet. I shall use one of these because it has scaling, but we only need positive numbers. So let's kind of hide this away. There and there. And do the best we can here. All right, will that be okay for you guys? All right, so time is x. 1 hour in, battery life is 80%. I hope you're good on this, like 8 being 80%. All good? All right, 80%. 3 hours in is 40%. 5 hours in is 0%. Looks like another absolute value. 6 hours in is 20%. 8 hours in is 60%. All right, looks absolute value-esque. Yes? Let's make it blue and get rid of that other arrow. So looks like an absolute value function. Okay. What type of function? Absolute value function. What type of function do you use to... Oh, I just answered that. Interpret the meaning of the x-intercept in this situation. This is the time for which your battery life is 0%, right? The x-intercept is 5 hours in and 0% battery life. That's the interpretation. So the x-intercept represents the time which there is no battery life. In this model, in this table, in this situation, model, whatever. In this situation, that is at hour 5. So why does the battery life go up after? I guess they're charging it. I don't know. I wish my battery charged as fast as it ran down for my laptops and phone and stuff. Oh, well, actually, no, my phone it does, right? It charges faster. Anyway, 2 more questions. Number 53. Let's go on to the next page. Compare each function with its parent function. State whether it contains a horizontal translation, vertical translation, both, or neither. Explain your reasoning. I don't plan on graphing them unless they ask me to. I think here they do want you to start working off the equations and making sense of what they have. So part A, we have f of x equals 2 times absolute value of x minus 3. Now, this compares to its parent function, which is f of x equals absolute value of x, right? It's an absolute value function. So what's different? The 2 is here, the negative 3 is here. How does it affect them? So does it contain which ones? Explain your reasoning. I guess I'm trying to read the instructions. I'm going to be more descriptive, but this is just based off how the numbers roll, right? This A contains a vertical... Wait, I don't know. It just talks about translations. It doesn't talk about stretches. I'm going to still mention it just so you can get the practice. There's a vertical stretch. I'm going to kind of bullet it. So there's a vertical stretch by a factor of 2. That's not really the part that we care about, though. We care about this part. There's a vertical translation. There's a vertical translation 3 units downward, right? So that's what's happening here. This is what the -3 is all about. So I don't know. That's kind of what I'm just going to do on these things. It's not really an explanation. I apologize, but I think we're going to be able to dive into these a lot more later. But the multiplication of the x value outside of it is the vertical stretch. This thing is outside of the absolute value part subtracted. There's the vertical translation. All right, let's go to B. B is a quadratic, and you have, let's keep that one up there, x minus 8 quantity squared. This is compared to the parent function x squared. Now, the thing in parentheses says that's something that affects your x values. That makes it a horizontal translation. And that's all that's here. There's nothing else on it. There's just a horizontal translation and a certain number of units. So, bullet point and bold it. We do a horizontal translation. 8 units to the right. I know I misspelled translation. 8 units to the right. This is due to the fact that I have to substitute 8 in for x to get 0. Something, we get to talk about later. I know my explanations aren't great. This is just, I'm not going to graph them right now. Is all. Part C. And again, I don't know what audience I'm reaching out to at this point. No one necessarily ever responds. Because sometimes I'll say this. I'll say, comment down below if you're still watching the video at this point because you're doing these questions. I don't know. I've never gotten a response. Maybe some people are like, yeah, I'm just listening to it while I sleep. Your voice lets me sleep. You are so boring that I sleep to your videos, Mr. Robinson. I've had students say that one way or the other. They're like, Mr. Robinson, your voice is so therapeutic. I don't agree. I'm not ASMR. Like, I don't have a microphone set up for it. I'm speaking in a very grating way right now. Your voice is so therapeutic that I can fall asleep to your voice. And then, Mr. Robinson, you're so... And the fact that students today, they have no filter, man. They'll just say what they think. Mr. Robinson, your voice bores me. I fall asleep to it. It's so monotonous. I don't know if they know that word. Okay, there are 2 things that are happening. You horizontally translate 2 units to the left. Now, this one's left because you got to substitute -2 into this thing for x, for the absolute value part to be 0. But it also translates vertically. You vertically translate 4 units up. So that answers a both, right? It's not just one, it's both. The last one, part D, 4x squared, that's 4 times x squared. That's with respect to a vertical stretch. You know, I probably shouldn't be putting f of x on this side here. They should probably get a different thing. But f of x equals x squared, parent function, multiplied by 4. There's no translations. It's just a vertical stretch. So this guy, vertically stretch by a factor of 4. No translation. No translation. So let me say this for C. I'll say both. And then this one, neither. You saw what they were before. Based on that. See, this needs some sort of like +7 or something like that to be like a vertical translation. Okay. Not deep on the explanation bit. I think it's more of once you start recognizing the equations for what they are. I think you're familiar at that point, if you're still listening. Last question, number 54, critical thinking. Use the values -1, 0, 1, and 2 in the correct box so the graph of each function intersects the x-axis. Explain your reasoning. What I find interesting about this is it reminds me of something you'd get in the cumulative assessment portion of your chapters, and that's not the case here. All right, so part A, part B, part C, part D. So part A says f of x equals 3x. I think that's raised to a power, to some power plus 1. Part B says f of x equals absolute value of 2x minus 6. Oh, we're definitely going to be getting into horizontal. Oh, hold on. That's a minus here. We're definitely going to be getting some horizontal biz later. Minus blank there. Part C, like horizontal stretches and compressions. F of x equals blank x squared plus 1. And then D, oh, they do say explain, don't they? Darn, I thought I was going to get away with it. F of x equals blank. Okay, -1, 0, 1, and 2. I think we have to use each one exactly once here. So I'm going to start with the bottom one. To intersect the x-axis, right, this is a constant, f of x equals blank. F of x equals -1, 1, or 2 would just be a horizontal line parallel to the x-axis. It would never intersect. Therefore, 0 needs to be this one. Okay? So by process of elimination, it couldn't be any of the other ones. Nothing else would intersect. That's my explanation. I'm saying it out loud. This is literally the x-axis itself. Y equals 0. It's just there's the x-axis, and that's the line as well. Okay, here's the first one. Let's look at this one next. F of x equals blank x squared plus 1. Now, when you see the x squared plus 1, x squared means a parabola, plus 1 means it would have shifted up 1. So to be blank times x squared means this is going to be something to flip it over. What would make it flip over? If it's negative. So we're going to have to make this one negative, which means this would be the -1. That's what would flip the thing over, so it could intersect the x-axis. I like this question as a whole. -1. Now it's down to two different things here. Let's look at this one because it's a more commonplace equation that we've seen. Should this be to the first power or the second power? Let's see what would happen if it was the second power. We just saw this before. This would be a quadratic, upward facing, vertex, one up from here, vertical stretch like that. It wouldn't hit the x-axis. But if it's to the first power, not that we ever see it as a 1 itself, but if it was to the first power, that would make it a linear equation. And a linear equation, even with a +1 y-intercept, that's a slope of 3, it would cross the x-axis there. So that should be the 1. Therefore, this should be the 2. Now, we might not know what this part means right here, but we do know, I'm not going to sit around and explain this one, but what we do know is this thing needs to now translate 2 units downward, and it's an absolute value graph, a positive absolute value graph. So as a positive absolute value graph, upward facing V shape, to shift down, whether or not you have the right spot on this, to shift down means it's now going to hit the x-axis in these parts, and that makes the 2 viable. The 1 would have also worked here, and I think that's what makes this one so important that we got to look at these all together. If I did put 1 here, this would have still worked, but a 2 can't work there, so I think it's nice that we went in that order. All right, and that's the last question. And guys, that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. This is the first section in the stuff, and I know that, I didn't use a table, and this was still over 2 hours, 20 minutes. Imagine me using tables as well. Maybe this will help me expedite the other ones in sections 2.2 and 2.5 or whatever else, whatever times we have to do certain graphs of these without use of a table, or how they're going to teach it. I don't know yet. I haven't really covered the books stuff with it, but I hope that they get into that tableless form so we can all agree together on how we do it. And I hope that everything I did here was good enough for you that you could use your own table or use your own graphing calculator, or you understood everything I said, especially if you had me for IM2 before. So this is just the start of chapter 2. Expect some longer things than from chapter 1 if you were along with me on those. And thank you so much for watching. Check out the description section below for anything else that you need from there. PDFs, graph paper, timestamps, and my playlist for IM3. So take care. I will see you in the next one.